I'll just start the proceedings. So, thank you, Professor Raichaudhry. First of all, I invite Dr. Anil Kothari to welcome Professor Shomak Raichaudhry from Ayuka. So, Kothari sir, I would request kindly welcome Professor Raichaudhry.
Sir, very good afternoon. I'm Dr.
Good
Kothari on behalf of whole organizing team. Sir, I welcome you, and it's really a great opportunity for us as well as all participants to have you as an expert in this prestigious program. So, sir, once again, welcome you and thank you very much for being with us in this program. Thank you, sir.
Thank you.
Thank you, Kothari ji. Thank you very much. Now I would like to very briefly introduce Professor Raichaudhry. So, Professor Shamak Raichaudhry has done his schooling and graduations from Calcutta and Presidency College, and then he has moved to Cambridge, where he has done a BA and followed by a PhD from from Churchill College, University of Cambridge, UK. Currently, Professor Raichaudhry is Director of Inter-University Center of Astronomy and Astrophysics in Pune, which we also known as Ayuka. Professor Raichaudhry has won several recognitions over the during his long career, and I will just share one or two with them as we have less time. So he has been recipient of Presidency College Gold Medal at University of Calcutta in 1982, Douglas Sheldon Essay Prize at Trinity College, Oxford, and he has also been awarded with the several fellowships such as Isaac Newton Fellowship or a scholarship from University of Cambridge, INLAX scholarship from INLAX Foundation from the University of Oxford, and there are so many much more. There are a long list. I will not take time to do that thing. It's my immense pleasure and honor to introduce Professor Raichaudhry to give this very interesting talk. Sir, floor is yours. Kindly enlighten us with the galaxy and the Milky Way. Thank you.
Thank you very much. Thanks, Dr. Shukla, for introducing me so kindly, and also congratulations to the organizers, everybody. Kothari ji for initiating this whole winter school on behalf of the Jenny Planetarium as well as Varamid Observatory, and for the faculty of IIT Indore for supporting this in such a very, very crucial way. I think it's been going very well, and I'm hearing from others how well this winter school has been going. I myself dipped into some of the talks already, and I will continue to do so. Thank you very much. So today, it's very short time. I'm supposed to talk about galaxies, which is biggest topic in the universe, in within 1 hour, and so I'll try and go a little fast. But my job is to introduce to you what galaxies are and how our galaxy plays a typical or atypical role among galaxies in the universe. You've already heard of galaxies in many other contexts before. There have been talks about AGN and several things like that. So I'm not going to go to that kind of detail at the beginning, but just let me introduce what a galaxy is first. And so what we do is, I mean, if you, what as astronomers we do is look at the sky through either our naked eyes or small telescope or large telescope. And if you take the contrast of the two pictures on this particular screen right now, you will see the right-hand picture is what you see with a naked eye or a pair of binoculars or small telescope. And what you see there are essentially all stars. They are stars, they twinkle, and this might not be the view from a very bright city, but if you go a little bit away from city lights, that's what you see. But if you take even a medium-sized telescope, and if you take it into space, particularly where the resolution is very good, then if you take a small blank part of the sky where you don't have many stars and you zoom in, on the left, this is what you see, and that's a little part of the Hubble Space Telescope Deep Field. And in this picture, there are only two stars, 1 and 2, the ones with the cross. And everything else is what we call a galaxy. Now, the difference between the right-hand picture and the left-hand picture is a galaxy has 10 to the power 11, 10 to the power 10 stars. And on the right, you are seeing each dot speck of light is only one star. And this was not really appreciated till about 100 years ago. And that is a surprising thing because we think of much of this kind of science being there with us for a long time. But I want you to imagine that when Rutherford was working on the atom or Einstein was working on relativity, they did not know that the universe is actually made up of galaxies. Galaxies are to the universe what molecules are to matter. They are the basic building blocks of the universe. And this is, historically, this is the only thing I'll say about history. Historically, this took us a long time to understand because we don't measure distances to objects very well in astronomy. It is very hard. And this is why, for example, if you look at the sun and the moon, they're the same size on the sky. You could imagine, some people will say, but they are the same size on the sky, same angular size, they're the same thing. And the only reason you know that the sun and the moon are not the same thing is that they are at different distances. So because we can measure distances to these things. And so here, I'm giving you examples of 4 things that look very similar on the sky to people who were working on this in the 16th, 17th, 18th centuries. And the naked eye, you would see things. There are some stars that look fuzzy. Small telescopes in the 18th century, a lot of interest was generated. And these 4 objects are taken from the catalogue compiled by Messier, Charles Messier, in France at the end of the 18th century. At the same time, William Herschel in England was making the same thing. He was trying to differentiate between the point-like stars and the fuzzy-like stars, the fuzzy objects in the sky. And they wanted to know whether these are different. Now, if you look at these 4 objects, they're all from both the Messier catalogue and William Herschel's NGC catalogue. And you will see that they're very different things. And you can see it because they are of the same size in the sky. I give the size in the minutes of arc here, and also give the distance that we know now to these objects. But at that time, maybe even 100 years ago, 150 years ago, these distances were not very well known. Here you have the Crab Nebula. We've heard of where such things come from, something called supernova. This is the product of a supernova that went off in 1054 AD. And this is a single star and the remnants of a star after it's exploded. In 1,000 years, it looks like this. M3 is a globular cluster which has 1 million stars. It is a cluster of stars. It is much bigger than the Crab Nebula, but it's very compact and it's got 1 million stars in it. Here you have M27, which is a planetary nebula, which is again a single star. But on the right here, you have M51, which is a 51th object of the Messier catalogue, same, and Messier thought all of these were the same thing. And this is a galaxy, and it's a whirlpool galaxy, and you can see that this is megaparsecs away, whereas this is kiloparsecs away, right? So it's 1,000 times more further away, and so on the sky they look exactly the same, and unless you have the resolution of a modern telescope, you can't really make out features in it. And this is why it took us such a long time to figure out that the universe is made up of galaxies. Even in the 1920s and 1930s, this debate was going on whether galaxies are stars themselves and the universe is a galaxy, or the universe is made up of small galaxies. But now we know that the universe is made up of galaxies, and there are many kinds of galaxies. About 20% of all galaxies, 15 to 20%, are nice and round, and they look very boring, and they are not very rotating. There's very little star formation going on in them now, and they mostly consist of very old red stars, and not much feature in them. About 75 to 80% of galaxies look like this. They are very flat, and they look like they're rotating very fast. In fact, you can measure that they're rotating very fast. And our galaxy is one of them, and they're called spiral galaxies because they have these spiral structures in them. They're disk galaxies, right? Now, these galaxies often interact with each other. They live in small groups, and as a result, they are islands in the universe, but they're not really islands because they often interact, they collide and merge, and do all kinds of things to each other. So, but they are the basic building blocks of the universe. Now, when this was first established through the seminal work of Edwin Hubble in the 1930s, who measured the first distances to these nebulae, to galaxies, he made this certain diagram to kind of propose how galaxies evolve in their age, right? And this you can find in every single textbook that you can find of astronomy, right? And he proposed that galaxies actually form in the form of nice round elliptical galaxies, and then they evolve into disk galaxies. They collapse and form disk galaxies in which you can see quite a lot of features. And so these are the spiral galaxies, and it's called the tuning fork diagram because he said that these galaxies would then divide up into two kinds, because some of these galaxies you can see have bars in the middle like that, and he thought that was a different type of galaxy. And so some galaxies would become bar galaxies and they'll rotate, but they have a bar-like structure in the middle. So he broke that up into two different classes. Now, even though this diagram appears in every single textbook of astronomy and galaxies and is taught in all introductory astronomy courses, this diagram is completely wrong in every way possible. In currently, what we know about galaxies is that, first of all, galaxies don't form as ellipticals and become spirals. In fact, it's the other way around. They form as disk galaxies to begin with from large clouds of dust and gas, and then they form and they actually collapse and start rotating very fast, because something that collapses, which has some angular momentum initially, as it collapses would conserve the angular momentum and keep rotating, and that would define a certain axis of rotation, and perpendicular to the axis they would collapse and form disk galaxies. And then we know that these disk galaxies interact with each other, they merge with each other, and so angular momentum is destroyed. And as angular momentum is destroyed, the rotational speed decreases, and the galaxies puff up and become more and more elliptical. So the evolution goes this way. We also know that there is no difference between the barred spirals and normal disk galaxies, because the spiral structure that you see in disk galaxies are actually transient. They last for a very small fraction of the lifetime of the galaxy, maybe 10 to the power 7, 10 to the 8 years, 10 to the several times 10 to the 8 years, and then they come and go. Similarly, bar-like structures also are transient features in rapidly rotating spirals. So some galaxies will develop a bar, and then the bar will go away, and then will come again in the lifetime of the galaxy. So these galaxies are essentially the same. So there is no tuning fork. And right now, based on multi-wavelength observations of galaxies from the infrared, from the ultraviolet, from X-rays, from optical, where we can study different components of a galaxy. Galaxy is made up of cold gas, which can be seen in the radio observations. It's made up of hot gas that it can be seen from X-ray observations. It's made up of stars, which can be seen from normal optical light. It is made up of new stars, very hot stars, which can be seen from ultraviolet, and then dust, which can be seen from the infrared. And you hear a little bit of the infrared and ultraviolet observations from Professor Ojha's talk, which follows mine. And you will see that all these are very crucial for us to understand what these guys. So this is a picture from the Spitzer satellite, which took infrared pictures of a large atlas of galaxies. And instead of the simple Hubble tuning fork diagram, it just shows how complex galaxies can be, and it shows how you have diversity in galaxies rather than having a single recipe for how galaxies evolve. So we now know that galaxies are very complex, and they change quite a lot during their lifetime, and they evolve from being disk-like galaxies rapidly rotating with lots of young stars into more round old stars, not rotating elliptical galaxies in their lifetime. and there are many different phases of the revolution. And if you're looking at all these galaxies, you are looking at, and this is why I showed you a picture at the very beginning of the whole diversity of galaxies. They are galaxies that are different parts of their evolution, right? We now know essentially you had many lectures about astronomy till now, and you know that the distance scales of the universe are now very well established. This was not, of course, true 100 years ago, and this is why there was confusion about which are stars and which are galaxies. We now know the average distribution, distance between stars is about a parsec, which is 3.25 light years. Size of a normal galaxy, 30 to 50 kiloparsecs, thousands of light years, thousands of parsecs. And the average distance between galaxies in the universe is about a megaparsec, a million parsecs now. And then the nearest galaxy to our galaxy, Andromeda galaxy, to our galaxy, which is the Milky Way, is roughly that distance, about 0.7 of a megaparsec. Our own galaxy looks like this, and so it's very interesting to study our own galaxy because we live in it. On the other hand, we can't take pictures of our own galaxy. These are artist's impression drawn because you cannot take a picture of our own galaxy being inside. But you can see that where we are in our galaxy, which is very flat, like a chapati, and it's got a bulge right in the middle. This is a typical of a young, newly formed galaxy. Our galaxy is not newly formed, but it's not as old as the universe. And it still has some stars forming, though it's not a rapidly star-forming galaxy. Just shows that it's not a newly formed, absolutely young galaxy, but it's a youngish galaxy. And here you are. We are a planet around a star called the Sun, which is about 8 kiloparsecs from the center, which is about 25,000 light years. And so from here we look at the universe. And so the picture that I showed you at the beginning of a picture of stars is because we are looking from here out into the universe, and we are looking at this thin screen of stars in which we live, and we're looking through that. And so if you look in that direction from here, we're looking in, I hope you can see my arrow. You can hear from here, if you're looking in these directions, you can see stars which belong to our galaxy, right? And you can probably see other galaxies which are out there, very far away. But if you're looking towards the middle of our galaxy, from here, then you can see a whole bunch of band of stars in the sky, and that is why it's called the Milky Way. And that is why in Indian languages we call it the Akash Ganga, the river in the sky, and that's because you can see the stars like that. Now, if you look from top on our galaxy, there's also again an artist's impression. You can see our galaxy has 5 of these spiral arms, and we are currently near one of those spiral arms. This is what the galaxy. This is actually a real picture. This is not an artist's impression. This is taken from Chile, a place where I go quite a lot, and it's very nice to see the plane of the Milky Way. If you're looking from here towards the center of our galaxy, you from the northern hemisphere, particularly north of India, from southern India, you can see quite a lot of it. The Earth blocks this part, but if you're looking in that direction, it's good to go to the southern hemisphere to see it, and you can see that is the center of our galaxy. And here is the center of our galaxy, Sagittarius, and a lot of dust in the plane of our galaxy. And in this picture, I mean, you can see the Milky Way itself, the Akash Ganga, is extremely bright. And on a night where there is no moon, you can read by this light of the stars. It's very, very bright. But there's another important thing in here, and that is from the southern hemisphere, you can see other galaxies with your naked eye very easily. These are the 2 nearest satellite galaxies of the Milky Way. They are called the Magellanic Clouds, the large and the small Magellanic Clouds. They are seen in the sky with the naked eye, and these are galaxies that are going around. They look like clouds, but they don't move. This is something we can't see from India, right? So you can see that this is because we are inside the Milky Way. We are looking out, and so we see this flat thing, which is the plane of our galaxy. But if you look at other galaxies, you will see exactly what our galaxy would look like from the outside. You can see that here's the galaxy which has 5 spiral arms. This is a different galaxy. There's a real picture. And if you look at it, you would see something like this, and then what happens is you can turn it around, and you start seeing the disk very nicely, and you can see the spiral arms. And then if you look in the edge on, you can see the dust lanes, and you can see that's what our galaxy would look like. This is another galaxy that is like our galaxy, very similar, but it's seen edge on. And if you take the center of that and blow it up, it's exactly what we see from our position in the galaxy, right? And this is an actual picture taken with an all-sky camera, which shows the Milky Way, and you can see how nicely it looks like an edge-on galaxy, as you would see any other galaxy, right? So we see these spiral arms very easily because there are lots of O and B stars which are young stars, because the newborn stars are formed in the spiral arms. They line up these spiral arms. There are not many spiral arms themselves, are not great enhancements in density, but they contain the brightest stars in our galaxy, because these are the hottest stars, the newborn stars, and these O and B stars illuminate the dust in these arms, so you can see it in the infrared, etc. And in normal light, you can see the hottest stars. So the spiral arms are essentially caused, actually they are transient features, just like as I said. They are not real features which are embedded in the galaxy. They are over densities in which stars, as they are moving in the galaxy, seem to linger a lot longer, and that is why you see these as can people mute their microphones, please? Thank you. Yeah, so this is a good analogy to understand, is that if you, for example, are traveling on a big highway, like the highway between Bombay and Pune, in which I travel quite a lot, you will find that there are places where traffic slows down and then speeds up again. They can slow down because if there's an accident, or maybe there's a traffic light, or maybe there is a toll booth where there is an obstruction and traffic slows down. So if somebody takes a picture of that highway, they will see that cars, there are more cars in certain places and not cars in the other places, because between those, the cars are moving very fast. In the galaxy, that's exactly what happens. As a star moves in the galaxy in a round orbit, it slows down around spiral arms, where the density is such that it allows the stellar orbit to be slightly different in there, and then it moves off this over density, and those places are seen as spiral arms. These spiral arms don't have the same stars all the time, just like on the highway, the over densities don't have the same cars all the time, but there are certain places, and so there's a pattern that evolves in the galaxy, in the disk of the galaxy, that stays the same, even though the sun or other stars move through these spiral arms and they're going around the galaxy, right? So here is, as I said, our galaxy has 5 different spiral arms, and the sun here is in the Orion arm right now, but it's moving very fast and it's going around. But as it goes into these spiral arms, it would slow down and linger a little longer, and then move much faster between the spiral arms. And that's how most stars are doing. The stars are moving in the galaxy faster than the pattern that you see in the spiral galaxy, right? So let's look at this question and try to do this little calculation. So for example, we can see that the sun is going around in the galaxy, and I'm just trying to figure out how many times the sun has gone around in the galaxy. So the sun, we can now measure, is traveling at a speed of 220 kilometers per second. It is actually in a mostly circular orbit. We can figure that out from the motion of the sun, and its mean distance from the center of the galaxy is about 8 kiloparsecs. So if you look at what the kiloparsec is in terms of kilometers, and you do a simple calculation, then you will see that just from this very simple calculation is 2 pi r divided by v, r being we are assuming it's a circular orbit, we use all the different conversions between kiloparsecs and kilometers, years and seconds, and you do this whole calculation, and you'd find that the time taken for the sun to go around once in this circular orbit is about a quarter of a billion years, right? But the sun and the earth, the age of the sun and the earth, we know is from various things, the ages of the rocks in the earth and things like that, is about 4.5 times 10 to the 9 years. So the sun has gone around the center of the galaxy about 20 times in its lifetime, right? And so that's very interesting, because think of the Earth along with the sun going around the galaxy so many times, how many different environments it has gone through. And it must reflect on the life of objects on the Earth, life of the Earth. And then there are lots of speculations about this. We can look at how climate has changed on the Earth as the sun has gone around the galaxy. We believe, for example, the dinosaurs died 65 million years ago due to a large number of asteroids that came and hit the Earth. Maybe that was because the Earth and the sun went through a particular part of our galaxy where the tidal forces caused this. Who knows? These are things that are speculations, that are nice theories that people try, but there are people who have done work on this. In fact, you had last week a lecture from Dr. Mayank Paya, who talked about the history of Indian astronomy. He'd done some really interesting work on trying to figure out where the sun has gone through in our galaxy, and trying to figure out how we can actually look at whether there are any effects on the Earth from that. Now, here is our galaxy. Our galaxy is then part of a small group, a local group of galaxies. Galaxies don't like to live alone. They like to live in small groups. Some galaxies live in very large clusters. Our local neighborhood, the local group, is essentially two big galaxies, like our galaxy, the Milky Way, and the Andromeda galaxy, M31, which is about, as I said, 0.7 megaparsecs away. And they're actually falling towards each other right now at a very high speed, about 120 kilometers per second. Our galaxy has all these little tiny galaxies, which are 1,000 times, 10,000 times, 1,000,000 times smaller than our galaxy, which you can call moon galaxies or satellite galaxies. We know about 40 of them right now. Here are some of them, and two of them you saw in that picture, remember? LMC and SMC, Large Magellanic and Small Magellanic Clouds. There are many others which can be very tiny. I'll show you some pictures of them, and they are around. Similarly, Andromeda also has about more than 40 such satellite galaxies that we know of. The last count I saw was 47. They are also going around, but we are discovering one of these satellites every other year right now, either our satellite, because they're very faint and hard to detect. So as we make more bigger and bigger telescopes, we are finding these satellite galaxies, and many of these are going around us. So you remember the Magellanic Clouds. This is a nice infrared picture, all sky picture, where you can see the two Magellanic Clouds. They are seen, but in the Magellanic Clouds, we know it is pretty large. It's got a bar in the middle. It's much larger than the moon on the sky. So it's very big. The Small Magellanic Clouds is also like this. You can see these tiny galaxies, the satellite galaxies, which often we call dwarf galaxies, don't have any regular structure. Often some of them are spheroidal, but many of them are very irregular. The Magellanic Clouds are irregular galaxies, and you can see that these are some of the other satellite galaxies of our galaxy, now taken with modern technology. And for example, look at the Fornax dwarf, which was discovered in the 1970s, 80s. But even then, it took if you look at them, you will probably think that somebody's fingerprint has gone on to that picture. Maybe it's very hard to find out how that there is a galaxy there. There can be very low surface brightness galaxies. And so now, one of the ways this is done, Mike Irwin started this in the 1990s in Cambridge. I'd worked with him quite a lot during my PhD, where what one could do is look at either photographs of the sky that are digitized or digital photographs taken of the sky with CCDs, and then you look at various statistical methods to figure out where stellar overdensities are around our galaxy and around the Andromeda galaxy. And you subtract very carefully one from the other and try to find out little tiny over densities like this to find out these low surface brightness galaxies. And this is why it's a hard job, and people are doing it more and more. With the advent of the Sloan Sky Survey, this has become very possible. And now with much bigger digital sky surveys like the Subaru survey and things like that, these are becoming a reality. Right. So the Sloan survey has discovered more than 20 satellites of our own galaxy just by having digital pictures, which can be then it's a very sophisticated statistical analysis can be done on them. From the Sloan survey, we also found this amazing thing. This is one of our satellite galaxies, the Sagittarius dwarf, and you can see it around the sky about 270 degrees. It is not just a little lump like that. That is just the star map of the Sagittarius dwarf. It's closer than the Magellanic Clouds. It's at about 25 kiloparsecs average distance. And it's actually what's happening is that this dwarf is falling into our galaxy. Our galaxy is pulling it in, and it's being tidally stripped to this. So as it falls in, it follows a circular orbit as it goes on, or elliptical orbit as it goes into the galaxy. As it falls in, it has angular momentum. And as it's coming in, the large galaxy that we are actually destroying this galaxy completely by pulling out its stars. And you see it in a trail along its orbit. Actually, the Magellanic Clouds, it is believed, were actually one galaxy, and you now see them as two, the large and the small Magellanic Clouds. And if you look in the radio, you can see the gas that has been stripped out of it, and you can also see it as a stream of gas that is all around our galaxy, almost 360 degrees. And so this is what happens to small galaxies that are orbiting large galaxies. They are tidally destroyed, and they all fall into the big galaxy. And this is how galaxies grow, how galaxies interact with other galaxies. Occasionally, it is going to interact with a big galaxy. So there are so many examples now with discovered in the last few years, 10, 20 years, of dwarfs being tidally destroyed by the larger galaxies. These are some examples of some galaxies in the Virgo cluster, for example. And in Andromeda, this is the Andromeda galaxy, which has, again, two prominent dwarf satellites. But if you look at a deep image, you can see how there are these tidal structures of stars that come from these satellites, that the big galaxy is causing all these stars to be pulled out of these neighboring galaxies. Now, when galaxies collide, the stars themselves don't collide, right? And you can have big galaxies colliding or small galaxies falling into galaxies. And when galaxies collide, then they often inspire episodes of star formation in other galaxies. These are called starburst galaxies. And sometimes galaxies can merge, and sometimes they are known as this process is known as cannibalism. We tend to anthropomorphize certain terms like this. Now, you can see this in observations that are not optical in certain spectacular ways. On the left is an excellent picture of a small group around the M81 galaxy, but taken in the 21 centimeter line with radio telescope. And you can see the same galaxies on the right from an optical picture, but it's a negative picture, right? So these are the stars. And so you can see M81, that's called M82. And this is another galaxy, 3077. And just looked at that galaxy, you wouldn't know what's happening in between them, the fact that they're interacting very closely. And on the left, you can see the cold gas, which emits the radio 21 centimeter line. And you can see how these galaxies are interacting with each other, pulling each other's gas out. I showed you pictures of the Andromeda galaxy pulling the stars out of nearby galaxies. Here's an example of a giant galaxy pulling each other's gas out as well. And so the gas itself plays a very important role when galaxies merge. Now, then you have the two major galaxies merging with each other. Such things happen very frequently. It is hard to just sit and watch this happen because it takes millions of years, but you can look around you and see many galaxies in different stages of merging and collision. Here's a very good example, the mice. It looks like two playing mice, but it's actually two spiral galaxies that are interacting with each other. And it's a wonderful thing to just try and figure out what's happening in here. And what people do is do simulations where they take the normal components of a galaxy like dark matter, stars, and dust and things like that, and try to recreate them. And I'll show you an example of a simulation that recreates this structure starting from two very normal looking like our galaxy disk galaxies. And here's an example. So here you have one very large galaxy and one slightly smaller spiral, and this is how you start. You can see these two galaxies going around each other, but also coming closer and closer so that they each start interacting with each other. And just look at what the stars are doing. You don't see the dark matter, but you see the stars, and you see, and there's gas and there's dust in these galaxies, and you can see how they, after going around once, in which it came very close to each other, these stars are ejected in the other direction, some stars are going in there, and this is a real simulation in which just the gravitational force between each pair of stars is calculated. And you can see how it creates a structure that looks very much like the picture that you see in the sky of the mice. And it's very interesting to figure out what the different orientations of these things are. If you want to try to find out where such a picture came from, and it goes beyond what will happen. So this is what the mice look like now, and that simulation takes it beyond what you saw that configuration form, and you can see what happens when they mix up. So I told you our galaxy, the Milky Way, also has a companion that is falling towards us, very similar size, about twice the size of our galaxy, Andromeda. It's 700 kiloparsecs away from now, and it's going to come and merge with us in about 4 billion years or so. And this is what it will look like. So I wrote a paper on this long time ago. And so this is a movie made by John Dubinsky, which starts off a quote from my paper. And then it shows how these two, the Andromeda and the Milky Way, are going to evolve as they come close. This is what's going to happen to our galaxy. That's our galaxy. Okay, it just and it's going to do very similar stuff with as you saw in the mice. And this is going to be 4 billion years from now. You don't have to worry. Don't lose your sleep over it. This is much in the future. And this is what the stars will do. They will merge together, go around a couple of times, and then no, the stars won't merge, but the galaxy itself will merge and become a really messed up thing, but slowly it's going to become a nice round object in several billion years. So that's what happens. And as I showed you, this is our galaxy now, and eventually that's going to happen. So in our galaxy, we know that right in the center, there is this monstrous black hole, which is 4 times 10 to the 6 times the mass of the sun. And then that's right here in Sagittarius, and there's a lot of dust in the galaxy, and there are stars. That black hole, of course, was the subject of the Nobel Prize this year, as you know, because there was, and you must hear about it in other lectures, but I just wanted to give you an example. There's a small star cluster right near the center of our galaxy in Sagittarius, and there were 2 groups of people who traced these stars over the last 30 years using adaptive optics and in the infrared to trace individual orbits of these stars. And this star, for example, S2, going around that central black hole, takes 15 years for a whole elliptical orbit. And from those orbits, one can fit Kepler's laws, relativistic versions, and come up with the mass of the black hole in the center of our galaxy, 4 times 10 to the 6 solar masses. So each galaxy has a supermassive black hole, which is of the order of 10 to the power 6 to 10 to the power 9 times the mass of the sun, right in the middle of the galaxy. Now, so these are galaxies, but how are they distributed in the universe? We will later on, Professor Somnath Bharadwaj is going to talk about the large-scale distribution of galaxies in the universe, and he will talk about the cosmic web. But I just wanted to talk about what's in there. I mean, what do galaxies do? And galaxies, as I said, don't like to live alone. They like They like to live in small groups or in clusters. So this is an example of a simulation of the distribution of matter in the universe. It's not the most current simulation. This was done about 20 years ago with lots of particles, gravitational simulation with hydrodynamics thrown in. And you can see that, so this is a computer simulation that shows the distribution of matter. And the way matter is distributed in the universe, it's distributed in the form of filaments all over the universe, not very uniform, even on 100 megaparsec scales. And this is called the cosmic web. And what happens is these filaments, on these filaments are galaxies, and these little things are groups of galaxies, and they travel along these filaments, and the filaments meet at the crossroads. There are these large clusters of galaxies, which can have hundreds of thousands of galaxies in them. And so this is an example of a cluster, for example, which will have about 100 or 1,000 galaxies. You can see the small groups falling in. So for example, our galaxy could be part of that little group of galaxies in there, that yellow thing. And we are maybe 20 megaparsecs away from our nearest cluster, which is the Virgo cluster, 15 to 20 megaparsecs away. And we are falling in there. We know from our motion that we are falling into the Virgo cluster. So this is, and we are, there are all these filaments that are going through, and Professor Bharadwaj will talk about this. So you can have groups that look like this, small groups, and most galaxies live in groups, but there are big, large clusters which look like this. And so eventually groups merge to form clusters of galaxies. And some galaxy clusters are very well studied. Groups are not so well studied because it's hard to study groups. But there are a lot of people who study clusters of galaxies, and these galaxies, and this is a good example of a cluster which has many thousands of galaxies. And you can see in the center of the cluster, they're mostly elliptical-like galaxies, which are very red and very little current star formation in them. As you go towards the periphery of a cluster, you see more and more disk galaxies, spiral galaxies, which are blue in nature. Now, what are these clusters and groups of galaxies made up of? They are made up of galaxies. They're also made up of stars in between the galaxies. I showed you many, many examples of galaxies pulling each other's stars out. They're also made up of hot and cold gas. And of course, they are made up of a lot of matter that you don't see, and that's dark matter. And that dark matter holds the galaxies together in a cluster. And this is something that we have known only in the last 40, 50 years, that these large structures, clusters, are actually made, are held together by dark matter. This is a very good example of what a very dedicated small telescope, and this is a small 1 meter telescope that is used for about 2 decades now to look at just the Virgo cluster of galaxies right in the middle of the Virgo cluster. And it just does that. It just looks at one target for many decades, and it builds up some of the deepest images. And so this is an image built by Chris Mihos and his group using a small Schmidt telescope in Kitt Peak. And you can see that as you look at the really low surface brightness features in between galaxies in the Virgo cluster, you can see almost all the galaxies are connected with these star streams. They're all pulling out stars from each other. So it looks like there's a lot of stars that don't belong to galaxies, that are traveling between galaxies because the galaxies are interacting gravitationally even at long distances. If you look at them on a normal picture, it will look like these galaxies are very, very different, are separated. Now, as I said, in between the galaxies, so here are pictures. Now that we are capable of observing the universe with many other kinds of telescopes, and throughout this winter school, you are hearing about radio observations, X-ray observations, ultraviolet observations, etc. You can see what these different things tell us. For example, we have been observing the sky in X-rays only for the last 40 years or so very well, and with imaging telescopes only in the last 30 years. And here you can see what these tell you, because here on the left you can see a picture of Abell 1689, one of the pictures I showed you earlier with the Hubble Space Telescope picture, and it's reproduced here. So this picture, all these things, the galaxies that you see are there, but the purple glow that you see is the observation with the Chandra X-ray telescope and imaging telescope. And so that shows you the X-ray emitting gas in the galaxy cluster. On the right, you can see just the X-rays. I haven't put the galaxies on it, just to show what clusters look like in X-rays. Now, what you're seeing when you're looking at the X-ray gas is the gas that is 10 to the power 7 degrees hot. And this gas comes from the fact that it's gas that is sitting, it's mostly hydrogen with some other elements in it. It's the gas that didn't go into making stars in the galaxies, or this is stuff that's come out of the galaxies. And this gas sits in the gravitational potential of the dark matter that holds the cluster together, and it sloshes around in there and becomes hotter and hotter due to kinetic energy being exchanged due to the potential energy of the gravitational potential energy of the dark matter itself. And so the balance between the two is described by the virial theorem, and you can figure out how much kinetic energy the components can have if they're sitting in a big potential well due to the gravitation of dark matter. So, and this gas is very hot, and it emits in the X-rays, and it is in between the galaxies. So, and the amount of the baryons in this gas is equal to, if not more than, the amount of matter in the stars in the galaxies. So we have to study that in order to understand the clusters of galaxies and the galaxies themselves. Zwicky was a very important astronomer in the 1930s who actually proposed, by looking at the Coma cluster, this is the picture on the right, and the motions of the galaxies in the Coma cluster, that actually clusters are made up of mostly unseen matter. He speculated that there is no way you can hold these galaxies together if there is the matter, the mass of the cluster is just from the galaxies themselves. And his idea was forgotten for a long time till we now can look at the hot gas that's in there from the X-ray observations. Also, we can use the virial theorem and the motions of the galaxies themselves, because now, for example, in the Coma cluster, we know of velocities, individual velocities, radial velocities of more than 2,000 galaxies. So we can easily use dynamics to figure out what the mass of the entire cluster is, not just of the galaxies, and we find out that it's more than 10 to the power 5 times the mass of the sun. Whereas if you take each galaxy and scale it by the light that you see from the galaxy by the mass of the sun, you would find that it'd be about several hundred times less mass in the galaxies themselves. So there is much more matter in the cluster, in the dark matter that holds the cluster together, that you don't see it. And all you see are these galaxies and the hot gas moving around in the dark matter. You can look at the X-ray gas and X-ray emitting gas, and you can see this amazing X-ray. Here is a picture where you can see the galaxies in negative right here, but you can see the gas that fills the whole cluster, and that shows you the underlying gravitational potential due to the dark matter. The X-rays also give you a mass estimate for the cluster, and it's like, as I said a few times, 10 to 15. There's another way, and this is my last topic. There is another very direct way you can measure how much mass there is in clusters or even in galaxies. And you might get other lectures on this, and this is called gravitational lensing. And what happens is that when you look at distant objects, you can see light coming from them, but as you know, light bends as it goes around, goes past massive objects, because space-time itself is bent, an idea that Einstein taught us 100 years ago. And so what will happen is that as you look at distant objects through a cluster of galaxies or a galaxy, and look at the light that is coming past these galaxies or clusters of galaxies, you can actually find a way of measuring the mass of the galaxy or clusters of galaxies, because that's what will bend the light. So for example, looking from here, you're looking at something that's very far away, and the bending light that goes through this cluster of galaxies will make the images appear to be distorted, And then you can see, for example, galaxies being bent into rings, which can be seen in the sky as distorted images, or you can see them in very high resolution images of the Hubble Space Telescope. You can see very distorted images. And here you can see the distorted images that you see, these arcs, gravitational arcs. These are all normal galaxies, but you are seeing them very distorted because the light that comes through the foreground cluster, which is these reddish galaxies that you see, cause the images to be distorted because the light bends. As the light comes and it's bending, our eyes sees them as distorted images. And from them, you can model how much mass is necessary for these distorted images to occur. This is a whole subject of strong or weak gravitational lensing, and this gives a direct measure of the mass. So from the X-rays, you can measure the mass of a galaxy. From the dynamics virial theorem, you can measure the mass of the galaxy or the cluster. From these, you can measure the mass of the galaxies and the clusters, depending on what you are modeling. And a lot of students now do this, and you can come up with an idea of how much matter there is in a galaxy cluster. And you can see, for example, all this particular image, one of my most favorite Hubble Space Telescope images, has more than 100 such distorted galaxy images. Each one gives you some information about the foreground mass, the mass in the galaxy cluster. And you're looking at galaxies through these clusters. It also tells you about the mass of individual galaxies. And now we know that individual galaxies have dark matter that are probably 10 times the mass of the galaxy that's in the stars and the gas. We also know that for clusters, that factor is about 100 to 200 to 300 times the mass that is in the stars. Now, the interesting thing is, if you look at these components together, the X-ray gas and the stars and the dark matter, which is mapped by gravitational lensing, you can put them together and you can see how they are related. And it's very interesting to see that often, particularly in the cases of clusters and galaxies that are in the process of merging, they don't follow each other necessarily. So here are 6 examples of recently discovered clusters. And you can look at here, and you can see the X-ray emitting intergalactic matter is in pink, right? Okay, so this is from the Chandra X-ray telescope. The dark matter that you can get from the lensing, which is here is by weak lensing, and you can see that's how they are in these clusters. And you can actually see the optical picture of the galaxies also superposed on them. And if you put them all together, you can see X-ray gas. The blue is the actual dark matter, and then you have the galaxies themselves. All 3, in some cases, seem to follow each other, and in some cases they don't. Right. So this is another very, very interesting way of studying why this is so, and how, in some cases, in particularly in the case of clusters merging together, how the galaxies feel the effect of the matter, and how the different components react to each other. And I'll stop by talking about one of these extreme examples called the bullet cluster, where in general it was found that the mass estimates of these clusters are agree, but actually where these things are is very different. So you can see that in the case of the bullet cluster, the mass, the dark matter, most of the matter, is very separated from where the hot gas is and the galaxies are, right? So this is an example of 2 clusters of galaxies that have, just like galaxies were colliding on a much smaller scale, these 2 galaxies are colliding, for example, in there. Clusters of galaxies themselves can collide. And as they collide, the mass and the gas sticks together in the middle, but the mass goes through and the galaxies go through, and they can go around many times before they settle into a very nice configuration. So this is an example of this kind of research that is now done in terms of how galaxies and then clusters of galaxies evolve with time in the universe. So when you look at all these galaxies, pictures of galaxies in the universe, you think they're nice and round and they're waiting for something to happen for billions of years. the entire universe is very dynamic, and galaxies themselves are going through rapid evolution in many cases, and the systems of galaxies, the groups and clusters of galaxies themselves are also going rapid evolution. And this makes it very fun. Our subject, astronomy, particularly observational astronomy that involves the different kinds of astronomy that you're learning now, just is starting off. It is very new. And with this new information that we get from infrared, optical, radio, and X-rays and gamma rays, putting together pictures to study these things, very dynamic things, is a very fun subject. I'll stop here now and see if people have questions. Thank you.
Thank you, Professor Raichaudhuri, for the wonderful talk. Now, I will request all the students and the other members, if they have any questions, they can write in the chat box, and even they can also unmute themselves and ask. So there are already one or two questions are posted in the chat box.
Okay.
Sir, would you like to take them?
Just let me go to the chat box. I don't have it up in here. Yeah, good. Yes, so I can see Shishanandi asking, can you shed some light on weak and strong lensing? Okay, so that's a subject. I don't know whether you've been giving a whole talk on lensing, but I'm not going to give you a talk now. I don't have time, but I just tried to, in a few minutes, explain lensing. What happens is that as light passes massive objects, it bends, and as you know, our eyes can't follow bent trajectories of light, so they think that the light is passing in a, just like here in a straight line, and so we see these objects somewhere else. This is exaggerated, of course. In real life, what happens if it's a very an extended object that's at a distance and light is coming to us and it's bent, then we see distorted images. So when we see distorted images, and sometimes we see multiple images of the same thing, there are many cases where you see 2, 3, 4, 5, even up to 9 images of the same thing, because the eye cannot follow, as you can see, the eye cannot follow the trajectories and sees in different places. That's called strong lensing. Weak lensing is a more useful method in where what happens is that even though you don't see very strongly distorted images, but statistically, the images of a large number of galaxies in the background would be distorted systematically because of the foreground cluster or galaxy that you're studying, and so statistically you can average over a large number of galaxies to figure out the trend in distortion, and that gives you a very important measure of small distortions, which means that you can measure this kind of lensing not just in the middle of clusters, but at the edge of clusters or at the edge of galaxies or for single galaxies. And this is a very useful tool in directly modeling the mass distribution in galaxies or clusters of galaxies. I'll say that, but please, there are a lot of resources on the web. Go and take a look. There are lovely talks also on weak lensing and strong lensing. So that's one. Let's see. Amit, would you like to select some of these? I mean, there are quite a lot of.
Yeah, sir. I think there is one very interesting question asked by Anirudh Singh earlier, which I very briefly, he has written 3 lines, but I will very briefly give you the question. He is asking how we know about the rotation of the galaxy, whether all the galaxy rotates in the similar direction or how they choose the direction of rotation. So can you enlighten us about this?
Okay, very, very interesting question. Actually, there is no, of course not all galaxies rotate in the same direction. Why do galaxies rotate? Galaxies rotate, the original theory was proposed by Fred Hoyle in the 1960s. It's very interesting. It says, if you have the net angular momentum in the universe is 0, right? The universe does not have angular momentum. But if you look at different blobs of gas and things that actually collapsed to form the galaxies, these things themselves had angular momentum, small angular momentum. And this angular momentum comes from tidal interactions between these blobs. Well, you do understand what tidal interactions are, right? Because if you have two big objects, then the sides of these objects that are near each other have different gravitational force than the far end. And so as a result, because of the difference between the gravitational interaction of the two ends, the two far ends and the two near ends, for example, and everything in between, you will find that the pull is different between different parts of these objects. And as a result, they'll start rotating, right? So tidal interactions cause angular momentum. And angular momentum, so each of these blobs will rotate in a different way, and all of these blobs, the angular momentum cancels out. Now, as a blob then collapses to form a galaxy, you know that angular momentum is conserved. So that as the size changes to smaller and smaller sizes, the spin rate, the angular velocity increases. This you know. So the direction of the angular momentum then determines whether it's counterclockwise or clockwise, whether the angular momentum is this direction or that direction. That's completely random. As I said, all of these have to cancel to make the net angular momentum of the universe to be zero. So which direction a particular galaxy is rotating then depends on the original cloud, the direction of the angular momentum it had, right? And so it is a very interesting question, and it's completely random. Now you also have asked a question about relativity coming into this, and you will find that the kinds of rotations galaxies have are tens or hundreds of kilometers per second, and this is much lower than the speed of light. And so relativistic corrections are not very important in here, in these measurements. So what we can do is that we can actually measure the rotations of galaxies very easily by looking at Doppler shifts, the Doppler shift difference between two ends of the galaxies, or you can look at the radio gas, the 21 centimeter line that's coming from the radio observations of galaxies, and that 21 centimeter line can show you the amount of rotation within the galaxy. If you take observations at different parts of the galaxy, or you look at the width of the line. And I've done this hundreds of times using both radio observations as well as looking at emission lines in the optical and looking at its variation along the slit. So you can measure these rotations very easily, and it tells you which direction a particular galaxy is moving, counterclockwise or clockwise, and there are equal numbers of each. Okay. I hope that understand. I hope that, and I actually showed you that the sun moving in the Milky Way, how to measure that, and how that tells you about how much it has moved in the Milky Way. I did that exercise earlier. Is there any quick last question before I leave it to the next speaker?
So would you like to take one more?
Yes, I'm here. Don't worry. Go ahead.
So there is a question that how we differentiate between the stars which are associated to the globular cluster and from a galaxy. So this is what is written. So if you
Can the person who has asked this question, can you explain what you mean? I don't understand the question.
I think Priyankar, or let me see.
Yeah, Priyanka. So when we look at the collection of stars, how do we know it's a galaxy and not a globular? Okay. Priyanka, I mean, let me give you an example. There is actually not much of a difference in terms of looking at a globular cluster has about 1 million stars, 10 to the power 6 or so, right? Our galaxy, the Milky Way, has 10 to the power 10 stars, or 10 to the 11 in stellar mass, that is. So these galaxies are much bigger than globular clusters. But you're absolutely right. There are dwarf galaxies that are 10 to the power 6, 10 to the power 7 times the mass of the sun. Very dwarf. And so what's the difference between a dwarf galaxy of that size and a globular cluster? The difference is two things. One is galaxies have dark matter. And so just looking at the dynamics of the stars within the galaxy, you will figure out whether there's extra matter there. Globular clusters don't have dark matter, right? And so the dynamics of globular clusters of the stars will be very different from the dynamics of stars in a dwarf galaxy of a similar mass in terms of the number of stars in there. And secondly, you will find that globular clusters are very tight. They are a few parsecs across, 10 to the power 6 stars in a few parsecs. Just looking at the profile of light in a globular cluster, you will find that they look very, very different from dwarf galaxies, which I showed you is extremely shallow and very extended, right? So just looking at the morphology of light in a particular system, one can figure out whether it's a galaxy or a globular cluster. Um, these things overlap also, right? Because there are some galaxies which are dwarf spheroidals that are 10 to the power 7 times the mass of the sun, and there are globular clusters which look very, very similar. So you have to do a lot of investigation to figure out what these things actually are. But in general, they can be distinguished.
Thank you, Professor Raichaudhuri. I'd like to thank you for giving a wonderful talk and accepting our invitation to give this talk in the winter school. We are really honored. Thank you very much, sir. Thank you.
Thanks very much. My pleasure. Thank you very much indeed. Bye.
Thank you.
Good.
Bye.
Thank you.
Bye. So we still do have 10 minutes for the next talk. Uh, Professor Ojha, would you like to just check the slides?
Yeah. Thanks, Amit. Yeah.
Thank
So,
you, sir. How are you?
yeah, fine. How are you?
I'm fine, sir.
I'll just share my slide.
Sure, sir.
Can you see the slide?
Yes, sir, we can see the slides. If do you have any movies in the presentation?
Yeah, so I have one couple of very short movies at the end. So,
Can we
those
just
are embedded on the slide only. So I
can
think it
we
should work. Yeah,
can you
okay, I'll
just
just
play it once? Yeah.
I think it's not working. Yeah, it's working.
Yes, we can see, sir.
Yeah, okay. Yeah,
Sure, sir. So, sir, we'll start at 4:45. So another 7 minutes. Yeah,
3:45.
3:45. Yes. So
Okay.
still we have 7 minutes.
Yeah, no problem. I will just keep it like this.
Yeah, sure, sure. Maybe you can make it full screen.
Yeah. Yeah.
Thank you, sir.
Now you see the full screen.
Yes, we can.
Okay. Thanks, Amit.
Approve. Do you have any announcements to make?
Me?
No, sir. To approve.
No, not right now. Yeah.
Okay. Thank you.
Sorry. Thank you.
So we'll convene back after 5 minutes.
Thanks.
But I request all of the participants to stay. But we'll start the session after 5 minutes. Good afternoon, everyone. I welcome you all for the second lecture of today's day. So the next lecture will be given by Professor Devendra Ocha from Tata Institute of Fundamental Research, Mumbai, and he will be delivering a talk on infrared and UV astronomy. I will welcome Professor Devendra Ocha. Sir, we are glad and delighted to have you here for this particular winter school and giving this talk. Very briefly, I'll introduce you. So, Professor Oja has done his graduate studies from the Kumail University and followed by the PhD from astronomy and astrophysics from Louis Pasteur University, France in 1994.
Amit, you are muted, looks like.
Oh, I'm sorry. I'm sorry. Okay, I welcome you all for the next session. Our next speaker is Professor Devendra Oja from Tata Institute of Fundamental Research, Mumbai. Professor Oja has done his graduation from Kumail University and his PhD from Louis Pasteur University, France. I would request people if they have, can they mute themselves? Yeah. So, Professor Oja's main research interest is multi-wavelength study of galactic star formation regions, galactic structure and kinematics of the stellar population of our own galaxy, and astronomical instrumentation. Today, he will be delivering a talk on infrared and UV astronomy. Sir, I welcome you to this winter school for this talk. We are honored to have you here for this lecture. Sir, floor is yours. Kindly deliver your talk.
Can you hear me?
Yes, sir, we can hear you, sir.
Okay. Thank you very much, Dr. Amit Shukla, for introducing me. And I also thank Dr. Abhirud Datta for inviting me to give a talk in this winter school. And good afternoon to all of you participants. So today I am going to talk about two aspects of universe, in one in infrared and other in UV wavelength. So I will mostly concentrate on my talk on infrared wavelength, and I know that during this winter school you are learning more about UV, and I think there are one more talk on space astronomy. So you will be covered more about our own UV experiments. So mainly I will concentrate mostly on infrared wavelength. And the outline of my talk is that I will introduce you UV wavebands and why those wavebands are important. And then I will go to the infrared wavelengths, and we will discuss here the invisible universe in those wavelengths. And then I will also show you all our own experiment which we are doing in infrared wavelengths. So these are the our own facilities which are available in India right now in different observational sites. So you can use those facilities because those facilities are open to users in infrared wavelength. Okay, so before going to in detail in my talk, and my talk will be basically on basic aspects, so very few technical slides will be there. So let's now discuss about exploring the universe. So you can explore universe either using particles like cosmic rays, which are basically observed when they bend by magnetic field in Earth atmosphere, or by photons when you receive photons from distant object. And then you can actually work on simple assuming that these are the black body radiation from stars or modified black body radiations. You can use different physics laws like Planck function or Wien's law. And if you work on those, you find that we have a very long range of electromagnetic spectrum where we can actually explore our universe. For example, if you go from gamma rays, so basically what you see here is the hot universe. You can study the hot universe because the temperature of the regions or stars or exotic objects which you observe are very high range of temperature. And then when you go to ultraviolet, this is the typical range of temperature of the objects you can explore. And so that's why it is called hot universe. But when you go to infrared, if you work out simply on the wavelength, because infrared basically roughly starts from 1 micron and up to 300 micron, we call it far infrared wavelength. And if you take these wavelength and apply on the Wien's law, you will find that basically the temperature of the regions which we are exploring in infrared is like 30 to 3000 degree Kelvin. So these are basically called the cool part of the universe. We call cool universe. And then if you go to submillimeter and radio, you are really exploring the very cool part of the universe. So these are the two distinct things which we discuss in UV in infrared. One is called hot universe, other is in cool universe. Okay, so that is what I want to emphasize in my talk. Okay, how you explore these two electromagnetic spectrum and what kind of object you see. So let's go first to the UV. Of course, before going to UV wavelength, just want to introduce, you might have seen this slide many times. This is the electromagnetic spectrum where y-axis is called atmospheric opacity and x-axis is the wavelength. So this opacity is just opposite of the transmission. So when you have 100% opacity, which means that you have a 0% transmission of the Earth atmosphere. So basically opacity from the Earth atmosphere. So if you see the left part of this electromagnetic spectrum, you see that Earth atmosphere is totally opaque in the ultraviolet range, even in X-rays or gamma rays. And of course, this tiny part where you see this rainbow color is the optical part. And when you go to infrared, around 1 micron and onwards, you see that some windows of the Earth atmosphere are transparent from the ground. Okay. Nevertheless, when you go to the mid-infrared and or the far infrared, which I call like beyond 100 micron, you have to go to the space above Earth atmosphere. Otherwise, the atmosphere basically blocks all the radiation coming from the distant object. So when you go to far infrared, either you have to do your experiment using balloons or you have to launch your satellites. So that is what we do in India. We have a balloon experiment and we carry out far infrared observations using balloons going above the Earth atmosphere like 32 kilometer or beyond, or you use the satellites. And in the near infrared, as I said, there are some windows which are transparent to the Earth atmosphere. So that's why we have a ground-based observatories in India, where we use in our own infrared instrument to explore the universe in near infrared, like 1 to 5 micron or so. And when you go to radio, Earth atmosphere is totally transparent, and that's why you can observe radio waves like GMRT from ground. Okay, so now let's go to the UV wave bands. So this easily accessible UV band from space basically lies in this wavelength range, which is like 912 to 3200 angstrom. So this wavelength range, again, we can divide in 3 different parts of UV spectrum. First is called extreme UV, like 70 to 900 angstrom. Then we call another window far UV from 900 to 2000 angstrom. And then we have a near UV wave band like 2000 to 3000 angstrom. So these are not really a hard boundaries of different wavelength, but these kind of boundaries comes depending on the availability of the detectors, like advancements of the detector. So it's very difficult to use one UV detector in all parts of electromagnetic spectrum. So that's why these kind of boundaries are made, where you can actually make use your sensitive detector in different parts of the UV spectrum. Okay, and then why this UV observations important? What are our motivations? So one of the biggest motivation of UV observation is that this UV part of the spectrum contains highest density of astrophysical information, either from the star or from the gas from which stars are formed. So I will come to that, which is called interstellar medium. So if you see in the plot, which I have shown in this slide, this x-axis is the energy in that particular band, like UV band, and y-axis is the number of spectral lines which you can observe from any object, either you take galaxy or star or so on. And I have binned these number of spectral line in per 100 angstrom interval bin. So this is basically the histogram. So one thing is very clear here that you see, as I said, UV contains highest density of astrophysical information, which, for example, if you see like in a lower part of this plot, means actually around the, you see that there is a large number of spectral lines which you can observe from the universe. Either you see these lines are either molecular hydrogen or like hydrogen deuteride kind of molecules, or even atoms and ions. So you see that the universe is rich of these lines, and these lines are actually falling in UV wavelength. That's why it makes very interesting to observe these lines or get information about the total energy budget of gas and dust in the UV part of the spectrum. Nevertheless, the most difficult part to observe in electromagnetic spectrum is UV because of the complexity of the detectors. So there is a chicken and egg problem here. You have a lot of information available in UV part, but at the same time, it is very difficult to observe in UV because you need very, very sensitive detector to observe in UV wavelength. Okay, so I will add more about UV observations. So another important aspect of UV observation is that the most important UV bright stars which you observe from our galaxies or other galaxies are actually the massive stars, more than the stars which has a mass more than, let's say, 3 solar masses. And these massive stars are very important because they are finally responsible for the elemental synthesis which happens in the molecular cloud. They are responsible for ionizing the cloud, dissociation, and many other energetic things which happen because of the energetic emanating from these massive stars. And these massive stars, that's why can part of the spectrum, like from massive stars, comes in the Lyman part of the spectrum. We call it Lyman, like hydrogen line of Lyman. These photons in Lyman part of the spectra are very energetic photons, and they can actually responsible for ionizing the region which we see in our universe, ionized gas, for example. And apart from that, I already mentioned, you can see numerous atomic and molecular spectral feature in UV part, like hydrogen atom, deuterium, so on, then molecular hydrogen. So you see all kinds of atoms and ions and molecules which actually can be observed in UV part of the spectrum. So this is about the gas. Now, if you go to the dust, again, the UV part of the spectrum is very sensitive to the dust. And of course, the bad news here is that the dust extinction, I will come to that later on in my slide. The dust extinction law is maximum in UV, which means that UV part of the spectrum is absorbed very easily by the dust. But nevertheless, this dust is actually gives indication that there is a dust in the interstellar medium, which can be probed in the UV part of the spectrum. And one of the very important feature which we see in this extinction law is called extinction peak around 2200 angstrom, which comes because of the lot of graphite dust which exists in the interstellar medium. And this is a very important feature, and that's why you can actually identify which kind of dust exists along with the gas in our galaxy. So it is very clear now that UV part of the spectrum is not only sensitive to the gas, but of course also is sensitive to the dust. So you can study both gas and dust, and then can study the whole energy budget of the universe in the UV spectrum of this thing. So and now you will see that why there are very few UV missions. So since the first UV mission, which was launched in 1978, was called IUE, International Ultraviolet Explorer, and the last one is our own UV mission. I mean, one of the instrument was UVIT, a UV imaging telescope in AstroSat, which was launched in 2015. So you will see there are very few UV missions. And as I said in the beginning, this is because it's not easy to develop detectors which are not different like CCDs, which you use in optical, or semiconductor devices which we use in infrared. Here we use photomultiply plates, and so on. So those are quite complex devices. So that's why you see very shallow part of the earlier satellite missions. Of course, Hubble Space Telescope is still observing, but other missions have very short life, and they have observed, and they talked about a lot of things about universe. For example, our own astrosat has now given a lot of interesting result in UV. For example, in this figure slide, you see a very nice image of globular cluster which has been observed with UVIT instrument in astrosat. And I just want to show UVIT has two telescopes. Of course, there are two major missions happened in last 1.5 decades. One was Galax, which was launched in 2003, and another was in astrosat. So advantage of astrosat, UVIT astrosat is that it has two telescopes of 37 centimeter diameter, which are shown here as compared to Galax, which has one telescope of 50 centimeter diameter. Another advantage of UVIT on astrosat is that it has a multiple filters in the available for UV observations, and whereas Galax has only two broadband filters. So if you have a multi-band filters, then you can actually trace different part of the physical parameters, like you can talk about temperature, metallicity, gravity, and so on, because different combination of these filters are actually tracers of different physical parameters of the particular object. And another advantage of our own UVIT is, as compared to the Galax, is that the angular resolution. So which are shown in these two panels, where you see that this is the image from Galax of some global cluster, and when you see in UVIT, you can actually resolve these stars in the global cluster and actually study individual exotic objects in this global cluster, lake type star like blue staggered stars or white dwarfs or so on. So you can actually pinpoint exact nature of these stars using our own UVIT. And as I said, multiple filters have many advantages. For example, this is one example which was observed with UVIT as a planetary nebula. And in these two panels shown here, you can see this planetary nebula observed with Galax in two filters. But when you observe it UVIT in multiple filters, you actually see not only the details about the nebula. For example, you see the red giant stars in the center and then ionized gas here. For example, if you take one of the UVIT color made from two filters, you can actually observe the ionized gas. So here the ionized gas is shown in carbon. This C2 is called singly ionized carbon, like hydrogen we call in S2, like astronomer call ionized hydrogen S2. Similarly, carbon can also easily observe in the interstellar medium, because carbon low ionization potential as compared to hydrogen. So you can easily dissociate carbon atom, and you can actually ionize carbon, so that you can observe these lines. And these are very good tracers to study the ionization properties of these planetary nebula, temperature of the nebula, and so on. So this is what you see in the UV universe. And now we have a lot of data from our own UVIT instrument, and some of you can actually work on those data and study different kinds of object in UV part of the spectrum. Now let me move to now infrared, where I will talk more about details about these infrared wavelength. So infrared light is basically discovered in 1800. You see this gentleman, William Herschel, and at that time, about 200 years ago, he called this infrared light as invisible light. So some of you know that his experiment, where he basically observed the sun rays which passed through the prism, and other side he kept a thermometer and he basically measured the temperature of the sun rays. And what he found is that its energy has all same characteristic as the visible light, but this light was not sensed by the human eye. That's why it is called invisible light. And then, since this light was discovered by Herschel beyond the red part of the spectrum, that's why we call it now infrared, basically red part of the spectrum. So that way the infrared light was discovered. And so what I will talk now is about brief overview of this infrared astronomy using in infrared wavelength observations. So there are two important aspects of infrared wavelength, and these are most important, particularly for studying the birth of the stars, how the star formation occurs in our galaxies or in other galaxies, and to study the interstellar medium, the raw material from these stars are formed. The advantage is that infrared wavelength, being at the longer part of the spectrum, can easily basically penetrate these obscure region. You see in the background, there's a spiral galaxies, and most of this this star formation is happening around this spiral arm of these galaxies. So you see these bright glow features like stars, and in between the material is called interstellar medium, material between the star. And these regions are quite obscured when you go observe them in visual or optical wavelength. That's why you see these dark patches here. So these dark patches are nothing but like dust, which we see in this kind of galaxies. And that's why infrared wavelengths are very important, because they can actually penetrate these dust regions in the universe. And I will come to that later on in my talk. So why this infrared astronomy or infrared wavelength is very important? As I already explained, you can actually observe the invisible universe, which means that which cannot be observed in optical wavelength. And then you can also explore the hidden universe. Hidden, I mean here like deeply embedded, where you have lot of dust and gas, where optical light will be completely obscured, and re-scattered light from the optical will be seen in the infrared. So you can observe these embedded objects, which are basically new stars which are formed in a star forming region or interstellar medium. Then you can detect cool objects, like the same way when you can observe young objects which are just formed in the star forming region. Same time you can also observe late type object which we call cool object, like red giant stars or asymptotic giant stars, because these stars at the end of their lifetime actually lose masses, and this material is basically collected around the stars called circumstellar disk. So when you have a disk around the star, again your UV optical or UV light is obscured there or absorbed there and re-scattered in the infrared. So that's why it's very easy to observe these late type of stars also in infrared. Then of course you can also explore early universe, which I mean is that when universe is expanding, which means that any line which you observe in optical will be redshifted to the in longer wavelength like infrared. So you can actually measure the redshift of the line, or basically suppose you are observing important line called hydrogen recombination light, like H alpha line, suppose at 6,000 angstrom in Milky Way galaxy, and if you go to the nearby galaxy, this line will be actually redshifted to the infrared wavelengths. That way you can observe these lines and talk about more about the properties of that region. So that's why you can observe these early universe, means nearby galaxies. And then of course you can add our knowledge of visible objects by observing infrared, which cannot be detected or discovered in optical wavelength. Okay, so now let's see whatever I talked about. Now I want to demonstrate why this optical infrared light is important. So in this slide, you will see here, this the left panel is the Orion constellation region. So what you see in this optical image is just the star. So this blue line is just to guide your eyes. And so as you see in optical wavelength, you just see the star. And this is a famous trapezium region. And as soon as you go to the infrared, like this far infrared, as I explained you, far infrared is like beyond 100 micron up to 300 micron. So you see completely different part of the same constellation. What you see here is a lot of dust and gas in this Orion region, and that is what we know about Orion region, where new stars are forming because of this raw material. So basically these dark patches are basically the dust, and the bright patches which see in yellow light are basically the dust which has been basically brightened because dust is shining because of the star which is hidden behind the dust. So massive starlight which has been basically penetrating through the dust, and that's why you see this ionized gas here, and some places you see lot of dust. So completely different part of the properties of that region you can study in infrared wavelength. Okay, so now based on these properties, now we can actually made a nomenclature on infrared wavelength, like from 1 to 300 micron. So as I said, infrared wavelength we can actually divide in three spectral regions. First one is the near infrared, which is basically from 1 to 5 micron. Then you have a mid infrared, like 5 to 30 micron, and then far infrared 30 to 300 micron. And in these different wavelengths, actually you can study different parts of the universe, different types of the object. For example, when you are observing in near infrared, you basically study the stars or dust, basically thin dust, like cool stars, like red giants. But as soon as you go to the mid-infrared, you can actually go much cooler regions. So you can study the planets which are forming around the stars or comets or asteroid, and basically the disk around the stars. And then when you go to the far infrared, you actually penetrate very cold dust, like in molecular clouds. So you can actually penetrate the central regions of the galaxies where you have very, very obscure dust, or like black holes kind of objects are situating there, very cold molecular clouds and star forming region. So these different parts of the electromagnetic spectrum are not the hard boundaries. These are again basically comes because of the availability of the detectors which we observe with the telescope when we observe in infrared. For example, near infrared detectors are quite different as compared to the far infrared detectors. So that's why, because of the advancement in the detectors and properties of the detectors, these different parts of the infrared wavelengths has been divided. And also near infrared wavelengths can be observed from the grounds, because some windows are transparent to the Earth atmosphere. So that's why we, as you know, we have many ground-based telescopes situating in different parts of the India, and from where we can actually observe in infrared using our own cameras or spectrometer. Okay, now I will come to this cartoon about our own Milky Way, and before I will go in detail about the infrared wavelength. So as you see in this right panel, this is the Milky Way galaxies seen as on view. It is the edge on view, and if you just see Milky Way as a face and view, then you will see it like this spiral galaxy in the lower panel. So what you see here in Milky Way, there are different constituents of the uh, 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 populations. So what you see, basically you see the disk around the central region where we have a galactic center. Then you have a bulge region and in the center of the galaxies. Then there are three different kinds of disk. And then you see the halo around this center region. So when I am talking about star forming regions, which are important for infrared wavelength, basically we are talking about the galactic plane of the disk, which is seen in the red color here. So these are called stream disk, where most of the gas and dust exist, and where actually most of the time stars are forming. Okay, so that's why this region is very important in galaxy, and I will concentrate on this galactic plane region of our galaxy. Okay, so in this galactic plane of the region, as I said in the beginning of my talk, we have a raw material called interstellar matter from which stars are forming. And so we would like to know how much of this ISM is there in our galaxy. For example, in this central region of our galaxy in the galactic plane. So we know from our observations done in molecular wavelength bands that 10% of the total mass of this ISM is basically concentrated in the galactic plane of our galaxy. And out of this 10%, 99% of the ISM actually exists in the gas component in terms of mass. So actually most of the ISM is in the gas component, and only 1% of the ISM is in dust components. Okay, so although this dust component is very tiny, only 1% of the total ISM, but as you see that this dust actually plays a crucial role in the interaction with the galaxy radiation field and so on. For example, this radiation field which is coming from stars and so on can be absorbed in this interstellar medium, and then it can redistribute this light to the higher energy like infrared wavelength. So in that way you can actually study the thermal properties of that particular region, and in that way you can probe the dust of the ISM material. So this dust is like a catalyst. It is very important, and very important in the sense that it basically acts like a catalytic agent when stars are forming. Okay, and this dust grain sizes which has been observed in interstellar medium range from 0.01 to 0.2 micron. Okay, so this is the properties of ISM. Now, of course, some of these numbers are observed numbers, and some of them are the analytical numbers derived from modeling. But let us see what is the evidence of interstellar medium in our galaxy? Do we know that this matter exists between stars or between galaxies? Between galaxies we call intergalactic medium. So we want to know if we can see these regions directly. Yes, we can see these regions. So this cartoon here is shown. This is the observed image observed in optical wavelength. So these are called false color image made by 3 optical bands. So what you see here, 2 colors. One is the blue color and one is the color in magenta. And we know that this blue color is, it's basically like you see the sky in blue color because of the scattering of the sunlight scattered by dust. So same thing here, the light which has been seen from this star, it is a bright patch here, is basically scattered by the dust, and that's why you see that lower wavelength, like optical wavelength, is scattered more, so you see more blue light, and that's why these are the evidence of the dust in interstellar medium. Similarly, if you go to this other region where you see this a very bright star, Sigma Sco, which is a bright star, and in this star is hiding behind the gas and dust. So this magenta color is basically the ionized gas, where for example, if you have a molecular hydrogen, which is the most abundant gas in the interstellar medium, which is ionized, basically you knock out 1 electron from the hydrogen, so we call singly ionized hydrogen. So because of the energetic photons which are coming from the massive stars as ionized this gas, so you see the gas there. So you clearly see in the same region, like this is the region in Orion, you see both evidence of gas and dust in the Orion region, which means that yes, there is evidence of interstellar medium in the in our galaxy. So this is the another example where now you see this famous region called a Horse Nebula or Dark Nebula in optical, again in Orion region. And this nebula which you see in a horse head is nothing but is like a dust pillar in the interstellar medium. And this is again because you see this dust pillar because the star which are basically hiding, which are not yet came out from this dust, are behind the dust and gas, and the radiation which is coming from the star is absorbed by the dust. So that's why in front, in foreground, you see this Horsehead nebula. So this is another evidence that yes, there is a plenty of dust exists in our Milky Way galaxies or interstellar medium from which new stars are forming. Now I will come to that why this infrared wavelength becomes very important. So now you see same Horsehead nebula in optical here. Now in this slide you see first one, again still you see Horsehead nebula in near infrared like 1 to 5 micron, okay, just beyond optical. And when you go to mid infrared like 5 to 20 micron, you hardly see this nebula, okay, but you see many stars. So star which were hiding were now seen in the mid infrared. Now when you go to the far infrared, you actually hardly see this Horsehead nebula, okay. So in this sense, dust becomes very strong in this region. So what does it mean is that, so when you go to the infrared wavelength, in longer wavelength, this region wavelength is able to penetrate this very obscure region of the Milky Way galaxies or interstellar medium. And once you penetrate this, for example, in far infrared, you can actually study whole dust properties. So that Horsehead nebula was nothing but a dust pillar. Now we see in far infrared, it looks like a uniform kind of dust feature in far infrared, whereas mid infrared you see the star which were earlier hiding in the optical wavelength has actually now seen in mid infrared. So you can actually study these very young stars, we call them baby stars, which have just born from the interstellar medium. This is another example I want to show beauty of infrared wavelength. Basically, what you see is one region in star forming region in our Milky Way. The top panel is observed in some satellite called Spitzer at infrared wavelength like 3.6 or 4.5 micron. And when you go to the same region in optical lower panel, you see very different morphology. Basically, you see some kind of anti-correlation between IR and optical wavelength, whereas we see like a cosmic mountains of creation, like you see kind of mountains. These are the dust and gas mountains which are seen in the star forming region, and in optical you hardly see these kind of mountains. What you see, lot of stars, and these stars in optical are not actually stars which are born in this star forming region. Most of these stars are the foreground star. These are close by stars. close by in the sense that when you observe from like your telescope, they are nearby stars and star forming region is much further away. Okay, so you see all these foreground stars, but when you go infrared, you see all kinds of details about the region. Okay. Now, another example of a beauty of infrared wavelength is that as I said, it can penetrate deeply inside the molecular cloud. So this is one example where stars have one massive stars have just born. So that's why it is called stellar incubators with massive embryos, in the sense that this star is just born inside this gas and dust cloud, and you see it has been covered by massive embryos of star forming region or interstellar medium. So once you go to the like 24 micron, like mid-infrared wavelength, you can actually see how the stars are forming and what kind of properties of gas and dust of these stars from this star is forming. So you can study the properties of their parental cloud from these stars are forming, and then you can talk about that if all stars form in same gas and dust kind of properties, or the properties of gas and dust are different in Milky Way galaxy, and many other questions which you can address in front. Okay, so now of course we can see the evidence of interstellar medium. Now let me go why we study the interstellar medium, why it is so important. Of course, first thing is that we want to understand star formation, because ultimately stars are forming from this raw material. So we have to understand the properties of this ISM. And in ISM, in star forming region like our own Milky Way, can be seen in different forms. Like you can see them in a large molecular clouds. For example, this cartoon I have shown here, this is a large molecular cloud, and within that molecular cloud, you see ISM in dense cores. These are the dense cores within the molecular cloud, which can form because of the contraction of this molecular cloud. And in this dense cores, basically the new stars are forming. We call them embedded protostars. So these stars are just not yet have reached to the main sequence. Like Sun is like a main sequence star, which are basically can do the nuclear fusion and so on, but these stars have not yet reached to the main sequence. So these are called pre-main sequence stars, and these stars are just born after they come out from the star forming region. So why these stars are shining? Because these stars are shining because of the contraction of the material around them. So basically, when they are contracting due to the gravity, then they can generate, I mean, you increase the potential energy, and that energy actually basically tries to, based on that, they sign these stars. So they have not yet reached to the nuclear fusion stage. Okay, so that's why they call protostar or pre-main sequence stars. And so now these are the properties of interstellar medium, and you can study them easily in infrared. But then one important aspect of this is about how do you know that we have to go to this wavelength and observe in that particular wavelength. For that, there is a very interesting and very important aspect is that which we call interstellar curve. I will come to that. So this is one technical slide which I am showing. So in astronomy, we call it interstellar extinction curve. So what does it tell is that basically this cartoon you see in this figure, y-axis is either wave number, or in the top you see wavelength, which is increasing from ultraviolet to infrared in this direction, and y-axis is called log of absorption, or in other terms we call extinction. And this absorption is nothing but when you are observing from you to some star, so the material between you and star which can absorb the starlight can be observed in terms of absorption, and the unit of this absorption is like magnitude. Like when we talk about the star, we call it the star of that particular magnitude. And you see that if there is a absorption of 5 magnitude, then there is a difference of roughly 100 in factor in the brightness, which means that if you are observing a star in optical wavelength, and if you go to the infrared wavelength, you can roughly see from visible to near infrared 5 magnitude of absorption, which will be basically decreasing, in the sense that you 100 times more flux you can observe from the infrared wavelength. Okay, so that's why this interstellar curve was established. This is based on observations. So what it immediately tells you that if you go from left to right, that when you go from UV to infrared, the interstellar absorption is decreasing, okay, in a linear term. So in UV, there is a lot of absorption. That's why I explain you it's very difficult to observe in UV. But when you go to the infrared, absorption is decreasing or extinction is decreasing. So longer wavelength can probe more deeper. That's why you have seen all those beautiful cartoons about star forming region where you see inside of the star forming region in the infrared, and that comes because of this principle of interstellar extinction curve. And this is very important in astronomy, which is used in many places. Okay. And now you see direct inference of this interstellar extinction curve in this picture of the Milky Way. This is the plane of the Milky Way, and the question is that does our galaxy contain only stars? So if you see this optical image, you will see yes, they contains mainly the star, but that is not true, because as you have already seen, these dark patches are nothing but the absorbing medium, and this image is taken in photographic plate, so that is in the optical wavelength, so a lot of light is absorbed. But same reason, if you go to the infrared, like some millimeter, so you see this beautiful image of the Milky Way where the center region is the galactic bulge, and then you see that galactic plane of this image, and some millimeter range is beyond infrared, and there actually you can penetrate the center region, like where black hole is forming, for example, and in that way you can study the center region of the galaxy. Okay, so this is just to show you the demonstration of that interstellar curve thing. Now I will go to briefly to the star formation in the Milky Way, where we study mostly the star formation in infrared wavelength. So before that, I will just tell about how do you form stars. Okay, so let's take an example of like our own sun, like star. So this is the cartoon. This is a theoretical concept. We cannot observe all steps of star forming region. So what you see here is that stars are forming a dark cloud, like shown in that panel A, where you have a cloud made of gas and dust. And when you go to the panel B, you see that this star is collapsing because of some disturbances, nearby disturbances, and because of the gravitational collapse, this cloud collapses, and then it can form the dense cores, as I showed you in earlier my slide. And within dense cores, when you go to this panel C, you can form the protostars. Okay, star not yet reached to the main sequence is the early cycle of the stars, and around that you see the material around the star in the form of the disk. So basically the material is falling from molecular cloud through the envelope to the disk, and from the disk to the star. And this disk is rotating, as you know, molecular cloud is rotating. So this disk also, because this material is falling from the molecular cloud, so disk is rotating. So what you see around this is the disk and the outflow. So basically the material which are forming is also thrown out in the terms of bipolar outflows because of the conservation of the angular momentum. You cannot take all the material and form the star, because then it will reach to some kind of a break of speed, we call it. So it has to throw the material, and we call this thrown out material either in a bipolar outflow or jet. And in this disk, basically, if you go to the panel D, you can form the pre-main sequence star, like T Tauri stars. They are early stages of the stars. And when you go to the E and F panels, then you can actually form the planets around the star. So these planets are forming around this circumstellar disk of the star. Sometimes we call them protoplanetary object disk of the star, where new planets are forming. Okay, so this is what is the concept about how the stars are forming in the molecular cloud. And now we can see a direct evidence of that. Of course, this is the theoretical concept, because we cannot actually observe all these stages from beginning to end in one particular molecular cloud, because you can see that time scales are really very different. A panel is at time t equal to 0, but when you reach to time panel F, then these stars are forming in like a 1 to 10 million kind of time scale, million year time scale. However, we can observe these star forming region and find out the evidences if that is true, that stars are forming in molecular cloud or not. So I can just show you one example. This is the molecular cloud. So the dark patch is called a molecular cloud. And why it is looking dark? Because you see lot of gas and dust in this molecular cloud, and this visible wavelength is not able to penetrate. And in this molecular cloud, we assume that stars are forming, and And as I already said, the stars are forming because of collapse of the core, and there are different properties of this molecular cloud. But as soon as you go to the infrared, you see lot of stars. And these are the new stars which I was talking about, pre-main sequence stars and or protostars. So this is a direct observational evidences where new stars are forming in the star forming cloud. Okay, and now this star formation now happening throughout the galaxy. It's not that in one particular molecular cloud. So the galaxy is vast, and all kinds of star formation happening in every part of the stars. So these are some numbers which tells you that there is a evidence of star formation happening throughout the galaxies. So based on the star count analysis, now we know from observed number in optical and other wavelength that there are 100 million stars in the Milky Way. So this clearly tells that there is a evidence of star formation throughout the history of the galaxies. Then this star formation occurs in molecular cloud based on like molecular cloud observation, for example, CO and other wavelength like millimeter wavelength. We have measured the masses of this molecular cloud. So we know that star formation occurs in molecular gas or molecular cloud. Then also we know that star formation occurs within the central 1 parsec of the Milky Way. So the center of the region, you know that star formation occurring, and most of you know that this Nobel Prize, which was won in physics in 2020, was about this black hole discovered in the center of the region, and this was discovered because of the rotation of the massive stars, which were basically formed in the center region of the galaxy. So more massive stars which are revolving around this black hole are actually formed from star forming region in the center region. So we know that center region also star formation is occurring, and also we know that star formation is occurring in the outer galaxies beyond the sun. So we know that our sun is located around 8.5 kiloparsec from the center region of the galaxies, but beyond 8.5 kiloparsec also we have seen observed that star formation is occurring. And also we know that star formation occurs in nearby regions. So I already shown you some example like Rho Ophiuchus cloud, which is very nearby cloud to us, and Orion cloud. So as you say, see that star formation is occurring everywhere in galaxies. And the other important thing is that star formation occurs not only these kind of gas cloud, but it also occurs in isolated and clusters mode. For example, if you see that lower panel, there's a low mass stars, lower than the mass of the sun is forming in the molecular cloud. The background, you see the molecular cloud, and just these baby stars have formed. And also you see the stars are forming in a cluster mode, like in a right panel. You see clusters of star, and all are these are young stars. So it's a very complex thing, star formation. It happens in isolated cluster modes, and everywhere happens. Now this is a very another technical slide. Now I have only this slide, which is technical. Now we talk about star formation rate. Means we should know how much star formation is occurring in a quantitative way. So currently what we have observed in nearby region is that the current star formation rate in our Milky Way is right roughly you are forming 3 solar type stars per year, 3 solar mass stars per year. This is the typical number. So if you assume that all molecular cloud is collapsing because of their own gravity, and if there is a pre-fall collapse, there is nothing to protect the gravity, then it is called 100% star formation efficiency. And if you work out on your formulas, you will find that the predicted star formation rate is like 130 to 400 solar mass per year. So this is clearly a problem. Means observed number is 3 solar mass per year, but what we predict from your equations is like 2 orders or more magnitude. So there is some problem. So which means that star formation is not 100% efficient. And what we know from our observation is that efficiency of star formation is not very large, like 2% in large molecular cloud, and in some embedded cluster like here, it is like a 10 to 20%. So which means that star formation is not efficient. So which means that all the clouds are not collapsing at free fall. If they are collapsing at free fall, then of course every cloud should form, all clouds should convert into the stars. So certainly there is a problem. Which problem is that you need somebody, something to support this gravity. Because of that, they are collapsing. So people have talked about many other properties which can control the gravity. Okay, so basically star formation is controlled by basically the turbulence. We call it turbulence in star formation. And so there is an interplay between the gravity and supersonic turbulence in the molecular cloud. So question is that what supports cloud when it is collapsing under their own gravity? So one important thing is that gravity is basically controlled by the internal gas pressure of the cloud. Cloud has a temperature and density, so it has its own internal gas pressure, so which basically balances the gravity, and sometimes we call this hydrostatic static equilibrium condition in star forming region. Then, of course, magnetic field plays very important role in star formation. It regulates the star formation. Of course, we don't know much about magnetic field. And then there are rotations, clouds are rotating. So as you have seen earlier, when stars are itself are forming, you cannot actually convert all the material which is falling on the stars to make the stars. Some material has to be thrown out because of the rotation or angular conservation, momentum conservation property. So those materials are thrown like in terms of outflows and so on. So this turbulence is very important. This turbulence can be generated by like externally triggered like supernovae or spiral density waves because of the differential rotation of galaxies. So they can generate turbulence. So all these properties basically regulate the star formation. That's why all these clouds, they don't collapse there is no free fall collapse. So these different properties basically controls the star formation. That's why you actually form star formation as a slow, shallow rate in our Milky Way galaxy. Okay. Okay. So let me now go to this slide. That is the summary of my this star formation slide. Is that this interstellar medium which we talked about or star forming region is nothing but is like a life cycle of the stars. So what I does it mean about this life cycle is that you see a cartoon here, interstellar medium made of dust, molecular atoms, which we talked about just now. Okay, made of dust and gas. From this, basically, when clouds are collapsing, forming stars, okay, star formation is happening. And when this star formation is happening, you are forming different kinds of stars. Okay, you can form like low mass stars or you can form high mass stars. Okay, and that star properties are, and these properties of the star which are forming depends on what kind of dense cores these molecular cloud can form and what are the properties of this dense cores, like what is the temperature, what is the density. If density is high of this dense core, they will form massive stars. Massive means 8 times the mass of the sun, and these properties of the dense cores will be like density will be low. They will form the low mass stars like lower than the mass of the sun. And based on the initial mass of these stars, they can go into different phases of this diagram. Massive star will become a red giant, and at that end it will explode like a supernovae. Okay, if this is a massive star like more than 8 solar mass, if a star will be a low mass star, then it will end up as a white dwarf or planetary nebula and so on. And the beauty of that is that at the end of this life cycle, when they explode like supernovae or planetary nebulae, all the processed material from the star is again thrown out into the star interstellar medium. So in that way, this interstellar medium is enriched again by the stars. Okay, so the star which are forming right now will basically form from the enriched material from the early generation of the star. So that's why we call this star formation cycle is a life cycle of the star. Okay, and we have now already I have convinced that stars is since star still exist in some number today, new star must be replacing other star in a continuous cycle, so that we know from our star formation rate, and so that's why we call it still a life cycle. But the problem is that this star formation or star birth actually still remains a highly theoretical astrophysical process. So that's why you need lot of observations or multi-messenger or multi-wavelength observations to observe these stars. So that's why we have a lot of facilities in India. So I will come to now our own facilities from where you can observe these star forming regions or any other properties or extragalactic object, extra galaxies and so on using our own facilities like in white color are actually basically our own ground-based facilities in different telescope like Himalayan Chandra telescope or Aries telescope. And also we have a GMRT from where you can observe in radio wavelength, you can observe ionized gas from star forming region. And then also some millimeter, now a lot of data is available like ALMA and so on. So using this multi-messenger information, you can observe star forming region or star forming galaxy, starboard galaxy. Okay. So I will briefly go quickly about what kind of facilities are there in infrared wavelength in India, and mostly these facilities are developed in TIFR. Okay, so we have like a balloon-based facilities. Then we are working on get satellite facilities. Then also we have a lot of ground-based facilities. Most of our instruments in TIFR instruments are actually now coupled with ground-based telescope, which are actually now installed in different telescope, different part of India. So in this slide, you will see we have a largest telescope now in India's largest ground-based telescope, 3.6 Devastal optical telescope in Nainital, shown in the right panel. Then we have a 2-meter Himalayan Chandra telescope in Ladakh, which is still the world's largest altitude, like 4,500-meter altitude, from where you can observe in infrared wavelength. And actually in the 3.6-meter telescope, there are two instruments in infrared. We call them TennisSpec and TIRCam2. I will briefly mention this in the next slide. Okay, so this is the one of the spectrometer of TIFR imager, where you can do both spectroscopy and imaging using this camera up to 2.5 micron of infrared. And this is the Hanley site, where there is a 2-meter telescope. Altitude is 2,500 meter, and this side is very good infrared because you are going higher in the altitude, so you will have less absorption from the Earth's transparent atmosphere. That's why it is important for infrared wavelength. And this is the TennisSpec, another spectrometer, very important spectrometer because it can observe simultaneously from optical to infrared wavelength, and like 550 nanometer to 2540 nanometer, or 0.5 micron to 2.5 micron, and it has both spectroscopy and imaging mode. And it is really a very state-of-art instrument which is just commissioned and now open to all the users. Like you can observe, if you submit your proposal, you can observe this using this TennisSpec instrument from Aries telescope. And with the same telescope, there is another TIFR instrument called TIRCam2. So this TennisSpec is actually mounted on the direct port, or this is the direct port, but there are 3 ports in this telescope. So TIRCam2 is basically installed in the side port, and this TIRCam2 is very important. This is because this is the only instrument which can observe beyond 2.5 micron from India. So basically you can observe in 3.6 micron. And one of the very important band which you can observe is called polycyclic aromatic hydrocarbon band, which are the photo-dissociated region in star-forming region, can be observed with this camera. So these are the facilities available for you. And now recently we are also working on satellite experiment, and this is the experiment which we have now proposed to ISRO, and now we have submitted our report, and we'll work on the flight model of this. So this will basically survey in spectroscopic mode from 1.5 to 6.5 micron of infrared wavelength. Of course, this is a small telescope, 30 centimeter with low resolution. Only you can do spectroscopy from 100 to 120 kind of resolution, but it can cover almost like 50% of the full sky. And we expect that this experiment can be launched in coming 2 to 3 years. So this will be another facility in infrared. The last one is the balloon experiment, which works in far infrared, like 158 micron, where we are observing this carbon line, singly ionized carbon line. So this is our own experiment. We have a dedicated facilities in Hyderabad, and this telescope has a diameter of 100 centimeter. It has been launched almost like 26 times since 1983. And this is still very competitive, and you can actually get more detail where you go to this balloon facility web page, how these experiments are done. And these experiments are also very good for students who propose some kind of experiment before you propose that to the satellite experiment. So balloon is a very good experiment where you can actually demonstrate your experiment before proposing to the satellite experiment, and that's why we are doing this experiment far infrared. So this is just to show one cartoon. This is a very big experiment. We have almost 100 centimeter telescope of, and the weight of this telescope is like 110,000 kg. And this is a huge experiment. You see, this is the telescope in the left part, and this is the balloon which carries this telescope. There is a huge balloon, like say 140,000 cubic meter is the volume of this balloon. Really a very big balloon. And total length of this experiment is like 200 meter. From this balloon to this uh, telescope is like 200 meter. And when this balloon is released, it just goes up and takes out the telescope, and then we do our experiment in far infrared. And I will just show you a quick movie about that, then you will realize how important this experiment. So now let me just show you two movies. I think this is the balloon launch where we do our experiment, not in infrared. This is for atmospheric science, and this is called static balloon experiment, because here we are just holding the balloon and launching the balloon. But the other big experiment are called dynamic launch, which will be the next slide. So this is this is not working. So let me show you the dynamic launch. So this is, you see, this is the balloon here, and the other part of this is our own experiment in far infrared. And so now this balloon has been released, okay, and it will go on. In between balloon, you see a lot of electronics packages which basically control the balloon and telescope. And there is a, you can see the signing part is the parachute here. And now it is, balloon is taking our own experiment, this telescope. Yeah, so this telescope has just released, and then it takes, the balloon takes to this experiment up to 32 kilometer above the earth. And at that point, then we start observing at 158 micron, which is the far infrared wavelength. And then we observe this carbon line, because there is no hydrogen lines in that part of this line. So next hydrogen abundant line is carbon line. So we observe that line in, because of the spectrum for own star forming region. Okay, so that's why I want to stop here. Thank you.
Thank you, Professor Ojha, for a wonderful talk. You discussed a variety of topics, considering from the role of dust in the infrared and UV astronomy, molecular clouds, and finally the star formation regions. Now the talk is open for questions. So if there are any questions, kindly raise your hand or you can type in the chat box, and Professor Ojha would like to answer some of them. You can unmute yourself as well and ask questions directly as well, if you wish. Professor Ojha, there is a question. The question is, can you explain the turbulence?
Yes, turbulence is basically kind of a disturbances which happens. This is like a waves flowing in the sea. So same thing happens in a galaxy or star forming cloud. So for example, one kind of turbulence where gas and dust actually can flow is because of the movement of our galaxy itself, because there is a kind of a differential rotation of galaxy. So inner parts are moving faster than the outer parts. So in that way, the gas and dust which are seen in the spiral regions are basically have some kind of turbulence because of the motion of the galaxy. So this is one kind of turbulence. The another kind of turbulence in a, now within the star forming region is because of the, for example, you have a nearby supernovae, and when this supernovae nearby supernovae shock waves, and because of the shock waves, whatever gas and dust is there will actually of a disturbances, and in the disturbances you can see kind of a turbulence. So basically that is what disturbance is basically. So I can show you one perhaps one example of actual turbulences when I am talking about. Just let me go to that slide. Yeah. So if you just go, for example, so in the first panel, what you see is a molecular cloud, which is quite homogeneous and isolated, and there is some kind of disturbance, okay, which is called shock waves. Let you assume that it is coming from some source has exploded nearby. So this super shock wave is approaching to this interstellar gas from right to left hand side. And once second panel, if you go, once it passes from this shock waves from one molecular cloud, is basically compresses this cloud, because once shock wave is there, cloud will try to critical part of its structure, so it compresses this. So because of this compression, there will be a kind of a motion in the cloud which continues until the shock wave passes completely from the molecular cloud. This is third panel. And then because of this compression and disturbances, then this densest part of the cloud will become gravitationally unstable. Okay, so that is the condition where star formation occurs, and there is a contraction. And once of the collapse of the gravity, then you actually start forming the cloud. Is happening because of the help of the turbulence. So this is the turbulence, and it's happening because of real picture you see. This is the real observation. Okay, this is a famous Trifid nebula in Orion region, and what you see here, all these kind of a structure, is basically because of the shock wave, which I told you here, has passed through this molecular cloud and structure, fractal structure, like a turbulent structure, and in the process, new stars are forming. And for example, one you see in that lower side, this is just a new maybe stars have formed, and already some stars have formed. So that is what I want to tell you. This is the turbulence. Okay, the turbulence.
Thank you, Professor Ocha. Yeah, if there are any quick questions. You can raise your hand, or you can unmute yourself, or type in the chat box. It seems there are no more questions. Sir, I do have one question regarding this balloon movie which you have shown. So,
Yes.
what are the security features are needed to launch these kind of balloons? These are huge balloons. So, is
So
there any
security
special
features.
security and clearance?
Yeah. So we actually need lot of security features. First thing is, of course, one our security feature is that since we are using hydrogen gas in balloons, because helium gas is very costly. So that is very important, but that is our own experiment. So we have our own. But apart from that, the most important part of these experiments are that you need a clearance from the ATC, air traffic control operators. So because when these experiments time we need to have a permission that there are no planes are basically flying in the nearby zone. So we contact the airport and so on. So that is the first security feature, that we need ATC clearance, that we have to flow only when there are no planes are moving. Number one. Number two is we have our own corridor of flying. So, for example, when we are flying from Hyderabad, Balloon City, we have a corridor given by flying in the city. Left and right, if you that we have flown 500 kilometer across. So within that window, we have to fly. So we cannot fly beyond that corridor, because then there will be a forest or rivers and so on. So those are the security things. Then when we fly, we have many security features embedded in our telescope, like GPS or GSM and so on. So we track our telescope when we fly, and we see which part of the in the region it's flying and so on, and that way we can control it. Yeah, so there are different kinds of security.
Thank you. Sir, there is a one connected question to my question, that how to control a telescope in when it is flying. So
Yeah, so telescope is controlled similar way you control your gamma ray telescope or you control your optical telescope. So basically the way you control your satellite. So what happens when you fly your telescope? So balloon is like a carrier. So balloon takes it to the desired, and in that height, then balloon it just carries the telescope. Okay, so based on the condition of the wind here, upper, we call it upper wind, it carries the telescope. However, the telescope is controlled by all radio commands from ground, like we send command on satellite or something. So we have commands to orient telescope in azimuth or elevation. So same way, I mean, we have a different sensor, like we have a star tracker, we have a CCD or this photodiode arrays. So in that way, telescope is pointed there, and then we have different sensor like star tracker controls the telescope, and the telescope is pointed to that particular directions. So control is done similar way we control the from different telescope.
thank you, Professor Oja, for wonderful talk and accepting our invitation for the winter school. Now I will request Bhupesh ji to take over. Thank you very much, sir, Professor Oja,
Thank you
for
very much, sir. Thanks, sir. Thanks.
Thank you, Dr. Uda sir. Thank you. Thank you, sir.
Thank you. Bye. Bye.
So,
bye.
okay. Good afternoon, everyone. So today's we have last talk by Professor M.K. Patil sir. Can you hear me, Patil sir, please?
Yes, Mr.
Yes.
Bhupesh ji. Yeah.
Yes. Okay. So today's we have last talk by Professor M.K. Patil sir on optical astronomy data analysis. Let me introduce Dr. M.K. Patil is the director and professor at School of Physical Science of Swami Ramanand Tirth Marathwada, SRTM University, Nanded. He is one of the founding member of the school. He obtained PhD in observational astronomy, specializing in properties of interstellar medium and star formation in early type galaxies. So Patil research interests include multi-band imaging observations of early type galaxies, astronomical image processing, star formation, high energy astrophysics, active galactic nuclei, AGN, feedback in galaxy cluster, AGN, variability, X-ray binary sources, multi-phase ISM in Galaxy, etc. He has published more than 50 research papers in international journals, presented more than 50 papers in conference, and has guided a number of research scholars. He has completed several research projects funded by DST, UGC, ISRO, and established research collaboration with scientists in lead institutes from India and abroad. He is working as a member of LIGO, EPO, LIGO India Mega Science Project, International Science Discussion Team, ISDT, of 30-meter telescope, TMT, Hawaii. He is chairman, Board of Studies of Physics, visiting associate of IUCA since 2003. He is recipient of University Best Teachers Award, fellowship of several bodies, and life members of several professional bodies. Professor Patil is actively involved in the science population program and has delivered several public lectures in English, Marathi, and Hindi. He was instrumental in the development of the state-of-the-art astronomical observatory, high-performance computational facility. He has been also working on various committees like the member of the management of Council of University, chairman of the Board of Studies in Physics, member of the Academic Council, member of the Incubation, Innovation, etc. So I welcome Professor Patil sir in your winter school.
Yeah, thank you. Thank you
Can
very
you
much,
talk to
Dr.
us?
Bhupesh Saxena ji.
Okay.
Indeed, it gives me great pleasure to be part of this winter school. Good evening to one and all. Mr. Bhupeshji, can you allow me to share my screen?
Yes, yes, yes.
Is the screen visible now?
Yes, yes, visible, sir.
Okay,
Yes, yes, right, it's visible, sir.
it's
Continue.
visible.
Mm.
That's great.
Yes.
Hello,
Yes,
can you
sir.
hear me?
Yes, 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 visible.
Okay, thank you very much. Good evening to one and all. Let me at the outset thank Mr. Bhupeshji Saxena. He is one of my best friend and he has been inviting me even for last program also. I also take this opportunity to thank Professor Abhirup Dattaji, who is one of the important member in organizing of this winter school, and all the members from MPCSP, IIT Indore, and IIA. Myself, MK Patil, I am from SRTM University and would like to discuss data analysis strategy and processes with you. The outline of my talk is like the following. Hello, can you see the screen?
Yes, yes, sir.
Okay. So the outline is the following. I shall be talking briefly about the instrumentation that is required in carrying out astronomical observations, and then I will talk about the astronomical data analysis process, which is the important aspect of my today's lecture. Then calibration of the data, standardization, deriving science out of the astronomical data, and I shall be sharing some of the scientific results that one can arrive by through the analysis of this astronomical data. By the way, astronomy, we know it is one of the oldest branch of the science, and that basically focuses, aims at studying the celestial objects such as moons, planets, stars, galaxies, and whatnot. There will be then number of objects which are, of course, excitements among the humankind since the last long time. As far as the formation of the universe is concerned, we all know that it has formed through a Big Bang analogy, and today we are here, wherein we can see the stars, galaxies, planets, and all other objects in our vicinity. The information regarding all these objects which we have obtained so far is through the observation. Okay, it is not an exaggeration, or rather, it is true that astronomy is the observational science. And what do we observe here? How do we observe? That is important. And we will see that this information is reaching to us in the form of the electromagnetic waves that are being emitted or reflected, scattered, or interacted by the objects which are lying in between the source and the observer. And these electromagnetic radiations, they are in fact the messengers. They are carrying a lot of information to us. So it is up to us to extract the science out of it, to derive some useful results out of it. As far as the electromagnetic radiation is concerned, I am sure this slide you might have seen quite a couple of times. It covers a very wide range of electromagnetic band or other wavelength or frequencies, all the way ranging from radio, microwave, infrared, visible, ultraviolet, X-rays, and gamma rays. Out of this entire spectrum, a very small portion, which is called as the visible band or optical astronomy, that is focusing, that is catering, and is this portion, wherein we have already noticed or rather seen that these electromagnetic radiations, though they continuously reach to us, but still there are some obstacles. We cannot receive all these electromagnetic radiations simply by putting our detectors or instruments on ground. Rather, our Earth atmosphere, that is blocking some of the component of electromagnetic spectrum. Okay, and we will be receiving electromagnetic radiation only in this a very narrow band, which is called as the optical band, and of course at some intermittent bands like that of the infrared and radio. About this infrared and near ultraviolet, Professor Oja has already talked with you, I suppose. Okay, so what does this electromagnetic spectrum, what does these electromagnetic radiations do? Rather, they arrive us in the form of the oscillating electric and magnetic fields, okay, carrying all sort of information which is being transmitted by that of the objects, celestial objects. Importantly, this information that is reaching to us is in the form of encode. Okay, it is in encoded form, and it is up to us. It is now required for us to decode it and derive the useful information which one can understand. So in reality, these electromagnetic radiations, they are nothing but the cosmic messengers, and they are continuously carrying out this information to us. As far as the data analysis is concerned, we shall be taking the digital images of the celestial objects like that of the stars, galaxies, and all other objects, and we shall be deriving science out of it. So what is basically a digital image? Digital image is nothing but some sort of information which is arranged in the form of a two-dimensional array of photosensitive detector, which is called as a CCD. Okay, so this information is rather having all the information regarding that of the position, such as x and y coordinates, and it is in the form of pictures of varying intensities and so on. Okay, so as far as the astronomical data is concerned, the astronomical data what we receive is in the form of electromagnetic radiations, photons basically, and these photons, okay, which are reaching to us, they carry all other information regarding that of the position of the object from where those photons have originated, the time of their arrival onto the detector, then the direction from which they are coming, the energy of the photons, which is of course dependent upon the wavelength. Okay, and in addition to it, they also carry information regarding that of the magnetic field, which is often measured in terms of what is called as the polarization and so on. Okay, so as far as the observation of the astronomical objects is concerned, that basically comes to us in the form of the electromagnetic signals, which we shall collect on the basis of with the help of some sort of instruments, and that information is either available in all these forms or a subset of it. Okay, so what are the observables? As I have already mentioned, the observables in this astronomical context, they are nothing but the position of the object. That means either you call it as the XY position in your detector, or alpha and delta, what are called as the right ascension and declination of the object in the sky. Then it also carries information regarding their brightness, their luminosities, okay, which we scientifically measure in terms of magnitudes, then color, chemical composition from which these objects are made up. So all these kind of information that is normally carried to us. Okay, so in order to decode this information, we need some sort of instruments, and the instruments include a telescope, which is again very important one. Then the eyepiece or some sort of detector, maybe a photometer, maybe a photographic plate. If you are interested in doing the chemical composition, then spectrometer is required. If you are interested in studying the magnetic field intensity or magnetic field distribution, then polarimeters are required. So these are some sort of instruments which we normally use. So as far as the observational astronomy is concerned, basically it comprises a telescope which collects the photons. Okay, then at the back end of it, there are some detectors like that of the photographic plate, CCD camera, or even our eye can act as a natural detector. So the function of the telescope, as you see, is nothing but to collect more and more number of photons, because we know light gathering power of an instrument or the telescope is going as square of its diameter or square of the radius. Bigger the aperture, you see this is called as the aperture, because at the back end there will be a mirror. This is a reflecting kind of telescope. So a reflector or mirror, which is called as a primary unit, that is placed at the back end, and all the photons which are entering through this window, they will be falling upon it, will be reflected back and will be collected again at the back end with the help of a detector. So light gathering power of this telescope will be decided by how big is this size. Okay, so we probably you might have seen in other talks that there are a variety of telescopes being used by astronomers. Okay, and the reason is that a variety of telescopes in the sense of varying sizes. Some telescopes are of 3 meter, 4 meter, 10 meter, even you will see that there is a 30-meter telescope underway. So what is the reason? Why do we use such type of big telescope? Is because to study the fainter object. Because if the object is at a very, very long distance, we shall be receiving a very few number of photons, and therefore the signal that we are collecting is of a very poor quality, and in order to improve its quality, we need such a bigger aperture. it also plays another role of these telescopes also play another role of resolving the objects. So the resolution of the telescope is again going as of the size of the telescope. And the third and not so important role that is being played by this instrument is nothing but it's a magnification. So astronomical observations require a telescope of this kind, then a detector of this kind, which is called as a CCD camera, and you see that hello.
Yes, continue, sir.
Yeah, and a couple of filters. So these filters are basically the optical filters because our objective is to study only the optical astronomical observations, and therefore I will be focusing upon these filters only. Okay, so the information that is reaching to us is in black and white form. We need to convert it into another very usual form, which shall be very much useful for us to derive science out of it. Sorry, there is some problem, I suppose. Hello? Hello?
Yes, sir.
Yes, yes. I hear you,
Is the
sir.
screen visible?
Continue.
Okay. Okay. So as far as the detector is concerned, ideally we expect a detector which have a quantum efficiency or detection capability of 100%, because each and every photon that is reaching to us is very important, and therefore it is required for us to get it converted into the usual form or the meaningful form, and therefore the detection efficiency should be as high as possible, which is called as 100%. Each photon should be detected as a delta function. If there is a photon falling upon your detector, only at that time I should get output. Otherwise, the output should be equal to 0, and that is the reason why it is called as a delta function. Uh, of course, I'm not just collecting photons at a single point. Rather, I need a spatial distribution in the two-dimensional form, and therefore I need to have the detector of a large number of pixels which are arranged in the form of a matrix. Okay, I must be in a position to get the information about the time of the arrival of each and every photon, because that is important, particularly in some type of objects which are called as the variable objects. So the number of photons that is keeping on varying continuously, and therefore the time of their arrival is very important as far as decoding of their information is concerned. Then we must also be in a position to measure the wavelength of the incident photon, because that gives me information regarding the energy and of course the polarization. So this is the ideal requirement of the ideal detectors. But practically it is not possible to achieve all these requirements, and nonetheless still we have some of the very important properties, characteristics of these detectors. And what are those? Are nothing but the detectors, the modern detectors, particularly the CCD camera, they have a very high quantum efficiency, as high as about 99%. And that is almost meeting our ideal requirement. Okay, then you see that as its quantum efficiency is more, therefore every photon will give rise to some output, and that is in the form of photoelectric effect or rather electron. So each electron which is generated in the detector, that will be tagged with that of the incident photon. As far as this two-dimensional array is concerned, we have an analogy of putting large many number of pixels okay, in the form of a matrix, and hence we can cover a wider portion of the sky. But as far as the last three components are concerned, okay, the arrival time of the photons, the energy measurement, and magnetic field measurement, we do not have such type of analogies, such type of features with it. Nonetheless, what is important is that we can take multiple frames of the same object at different times with some intervals in between, and then by comparing the signal that is arrived at us, we can get the information regarding their variabilities and other things. Again, as far as the energy measurement is concerned, we do not have such a detector, but at the same time, we can use multiple filters, which I mentioned earlier. And by making use of the observations, by performing observations, by inserting such different filters in between, we can also get some sort of information regarding their energy. And there are some analyzers or polarizers with the help of which we can do the polarimetry and therefore magnetic field study. So remember, though these are the requirements and these are the achievements, still we will find that there are a lot many factors which affect our observations. As far as the construction of the CCD camera is concerned, they are the photoelectric effect based detectors. When photons fall upon it, they generate electrons, and those generated electrons will be stored under individual pixel. These are nothing but the pixels, and under the individual pixel, these electrons will be generated and they will be stacked up over there. Depending upon how many photons are incident upon this particular pixel, the number of free electrons which are generated, that will vary. Okay, so in other words, the incident photon, number of incident photon or intensity of the incident photon, that can be very easily measured by quantifying the number of electrons that are generated in each potential well under individual pixel. So this working of this pixel is not only to generate electrons but also to collect them. Once they are collected, then we can transfer it to the computer, to the various technologies, particularly the charge transfer analogy is being used. It is similar to that of our rain gauge instrument. We know rain gauging is normally done in this way. We put some sort of measuring calibrated measuring units, cylinders, and we collect water, and then finally we measure the content of each of the unit and take the average of it. In the same way, the photons which are falling upon individual pixel, they generate the electrons underneath it, and they will be transferred to the computer through what is called as the charge transfer devices or on-chip amplifiers. So as far as the images are concerned, using this instrument like telescope, detector, and filter, we can take the CCD images and then we can do lot of science with it. So what is the science that we can do? I will be explaining in following slides over here. So this is a typical CCD frame which is taken with the help of a telescope, okay, and a CCD camera. Of course, at that time, the shutter of the telescope was closed. That means no photon was allowed to fall or enter into the telescope, because we wanted to see what are the responses of the individual pixel within that CCD camera. And for that purpose, we need to take some calibration files, calibration frames. And these calibration frames are nothing but the bias frames, dark frames, and so on, which I shall be discussing in detail as we go ahead. However, though this telescope is still covered and no photon is allowed to enter into the CCD camera, still you see that there are some points, some isolated pixels which gives rise to a very high output, and these are covering individual pixels or at the most 1 or 2 pixels on the entire CCD chip, and they are normally regarded as that of the cosmic rays. If I take the CCD image, if I take image of some of the celestial object like that of the galaxy, it looks something like this. But when I look at this image carefully, I do find that there are several defects within it. So there could be dark columns like that of what we noticed over here. There could be bright columns also. There could be hot clusters of pixels. There could be several such unwanted signals. All these will be interfering with that of the signal that is coming from that of the object of our interest, and therefore that will be what we can call it as creating lot of noise in the scientific frames that we are interested in. So basic image processing, what I shall be discussing henceforth, is nothing but the CCD. This is a typically raw image that is taken with that of the telescope and CCD camera. So every pixel, you see, it is nothing but a M by N matrix of the individual pixel, which I already mentioned. And all these pixels are working as an independent detector. Now, once it is exposed to the sky with the help of a telescope, with the help of a given filter, it records the information in this form. So what is this information recorded in the signal, in the CCD, is nothing but the sum of various components. So it accumulates the light coming from that of the astronomical object, which is of course of different intensity. And by measuring the intensity of that individual source, we can do lot of science out of it. We can derive their flux. We can derive several other interesting facts out of it. In addition to that of the objective of finding out the brightness of the object, there would be unwanted signal, unwanted electrons which are generated within the CCD camera, and maybe because of the background light. Because if you see, if I expose my CCD, if I direct my telescope to the sky, you will see that in addition to that of the object of my interest, there will be lot many photons coming from the space, and they are either coming from that of the atmosphere because of the scattering of the light within the atmosphere, or even from the background objects, and all they will be contaminating our CCD. In addition to it, there will be cosmic rays, which I have already mentioned. We are operating these CCD at some elevated voltages. We are applying some offset voltages, and therefore they will also be generating some signals. Then there would be the noise which is generated because of the thermal agitations, which is called as a dark noise. Okay. Then there will be some other defects, cosmetic defects onto the detector as well as telescope, which will be yielding into such type of fringes, such type of vignetting effects, and so on. So this is raw CCD image is basically nothing but our data, astronomical data, and which is comprised of these two components. One among them is the signal, and another is the noise. If you look at the contributions, you will see that the signal is a single one, whereas the noise is contributed by multiple, or rather several such factors. And it is required before arriving at the science, because before deriving science out of this, it is required to take care of these unwanted components, and that is what is called as the image processing. So image processing is the process in which we shall be cleaning our images, okay, raw images, either by subtracting bias frames, by subtracting dark frames, by dividing them through the normalized flats, by removing the cosmic ray events, improving the signal to noise ratio. Then simply cleaning is not sufficient, because the data what we shall be having is our own data, or rather is the data which is acquired with the help of the given setup of observation, telescope as well as detector. If I want to compare this data with that of the observations made by another observer using other telescope and detector, then we cannot readily do it. We have to do some sort of other processes, and that is what is the calibration and standardization of the data. And then finally we can arrive at detecting the objects in it, either in an interactive mode or in automated mode. And then finally we can do the scientific measurements through the process of what is called as the photometry. So as far as the image processing is concerned, it gives us some kind of information, something like this. So I see there are number of objects in a number of information that is embedded within the given image. But I do not know what is the exact information, what is the exact meaning of that information. And for that purpose, I need to do a lot of processing of it. And once I do the processing, then finally I will be arriving at a beautiful science out of it, and I can get the perfect information regarding that object of our interest. Okay, so the information which is present in the raw image is in scattered form. It is required to be arranged in systematic way, and then we can arrive at the science. So how to do the images, and what are the important tasks that we need to do? So we need to display them. We have to physically examine each and every image very carefully and see what are the problems associated with it. Then identify those problems, recover them, overcome over them, so on, either by plotting line, column, surface plots, and so on. Okay, not only that, we can take multiple images of the same object or different objects, and we can do lot many arithmetic operations such as addition, subtraction, okay, and division, and so on. But you see, whenever I'm taking multiple images of the same object, you see, because of the several reasons, the image, the positions of the object in the same telescope and in the same detector, they appear to be slightly shifted. And therefore, before adding them, we have to take care that they are properly aligned. Okay, and that is what is called as the astrometric technique. Then we can do the image statistics, we can smooth them, we can filter out unwanted components, okay, we can detect the objects, we can do photometry of the objects, we can identify the different objects such as whether they are stars, galaxies, groups of stars, groups of galaxies, and so on. Okay, so for that purpose, we need to make use of the computer programs which are called as packages like that of the IRAF, APE, MIDAS, and so on. Okay, as far as the optical data analysis or processing is concerned, normally this is one of the very important package that is readily available and is called as the image reduction and analysis facility, which is abbreviated as that of the IRAF. It itself is a huge collection of so many sub packages within it. It does a lot many processes, okay, like that of the display of images, like that of the import and export of the data, display of images, cleaning of the images, fitting various functions onto the images. Okay, not only in optical, but you will see that there are some sub packages which can handle the X-ray data, even ultraviolet data, and all other data which are acquired using the other telescopes. So the data reduction starts with this first step, which is called as a bias subtraction. As I have already mentioned, our CCD is to be operated at some positive voltage. Okay, because if we are not applying any voltage to individual pixel, normally the counts what we shall be getting may be sometimes equal to 0, sometimes it may even give rise to negative counts when it is transferred to the computer. And in order to avoid this, normally some bias is applied, and this bias basically is nothing but the voltage which is applied to the individual pixel. And you see that here each dot what you can see is nothing but individual pixel, and you will find that if I run my cursor onto individual pixel in the IRAF package, I will get the information regarding the count of that particular pixel. And I see that that count is not constant always, rather it is completely, it is showing a lot many variations. Of course, these variations are within the acceptable limit, and that's why such type of frames, they are called as the bias frames. And we need to subtract such type of bias frames from that of your science frames as well as the flat frames. Then is the flat frame. That is another very important step as far as the calibration and transformation of your data is concerned, and that is called as the flat fielding. So what is flat fielding? Basically, what we do here is the following. We expose our CCD to a uniform source, assuming that every pixel in our CCD camera is receiving the same number of photons. Ideally, I expect that the response of each pixel within that CCD must be same. That means I must get a uniform image throughout. But if I look at this image, which is taken with that of a given telescope and a CCD camera, okay, this is called as a twilight flat. Okay, you see that the response of each pixel is not same. You can see lot many variations within it. Not only that, there are some regions, there are some spots which are called as the fringing effects. You can see again some variations within it. If I plot a line or column graph of all those pixels which are lying in a particular row or in a particular column, then it shows such type of response. You will see that the response of some of the pixels is very, very poor, whereas response of some of the pixels is significantly high. Okay, it is a normalized one. So ideally, I expect that each and every pixel should give the same response equal to that of 1. But here you see some of the pixels, they are giving very poor response. That means the count level or the response is lower than that of 1. And at these points, you see the response is very high as that of 1.05 or so. So why it is so? And there are several reasons which are called as the cosmetic reasons, or maybe some defects associated with the individual pixels also. But if such a variation is seen in that of the CCD camera, can we use it for obtaining a useful or fruitful information out of it? That is the biggest question. That is the biggest challenge. And believe me, we still with the same CCD, we can go ahead and we can derive the beautiful science out of it. And how it is done is just for the illustration purpose. I am making use of this slide. So this is your flat frame. You see that the response in this pixel, in this pixel, in this pixel is different. Here also it is different. White means better response and dark means a poor response. And here it is an intermediate response. Now, if I take this CCD and take the image of an object of celestial body like that of something like this one, so I'm not sure what kind of object it is. Okay, you see that here is completely dark portion, and therefore I may be in a I may assume that there is no signal arriving at this part, arriving at this part, arriving at this part, and so on. But at the center, if I can see, yes, there is a lot of signal that is received or rather is picked up by the detector. But believe me, this is not a good image rather. So how to derive a good image out of it? The process is a very simple one. What I can do is this one. If I divide this image by that of this normalized flat frame, before that, of course, I have subtracted the bias frame also. Also, I have subtracted the dark current. So when I divide this by this, I get this image. This is the resultant image. And you see that the response is very good. So this is the final image what I am looking for. And if I look at it, I will get a lot of information. I can see that it is not a object like that of our star, but it is an extended object with light distributed over this much portion. Of course, this light distribution is not uniform. At the center, it is having a maximum intensity, and as I go outward, the intensity is dropping systematically. The drop in this direction, drop in this direction, and in this direction, if I can compare, it is not same, symmetric rather. And therefore, it would be carrying heat, rather holding a lot of information. So our objective is to find out what is the reason why this kind of information, or why this variation is seen in even in the same image of the same object. Right? That is the beauty of the image processing. Then at the same time, you see that there are individual pixels which are heated up by what is called as they are hit up by the high energetic charge particles, which often we call them as the cosmic rays. But one important or interesting thing of these cosmic rays is that the effect of these cosmic rays is confined to individual pixel, and there is no spread or that of the overlapping of the information with that of the surrounding. Okay. So here is a comparison of our raw image, and here is an image, means the cleaned image. So what I have done on this image is nothing but I have subtracted the bias frame, I have subtracted the dark, I have what is called as the flat field edit. Then I removed the cosmic rays, I removed even the background also, and finally I arrived at this particular image. And this is a very important image, or rather a very smooth image, cleaned image, which is useful now for deriving science of individual object in it. You see there are number of point like white point like spots here, and these are nothing but the stars, individual stars. So I can do photometry of individual star, and I can find out their information. Okay. Again, another one important aspect which I wanted to share with you is nothing but the signal to ratio. Why the signal to noise ratio is important, and why the size of the image, or rather telescope, is important, and at the same time why we need to integrate the information over a longer time in order to illustrate it. I'm making use of this slide. So this is some image of the sky which is taken with that of the telescope and a CCD camera. I see that there is a spot or there is some white spot somewhere here. There are some isolated points somewhere here. Otherwise, it is a very noisy image. If I take image of the same region of the sky, but increasing the integration time, that means I am exposing this CCD for a little longer time, and then I find that it is now popping up, rather it is giving rise to some sort of, again, very interesting information which otherwise was not possible in the former one. So why this is looking much pretty compared to that of the former one is because you see that the noise which was present in the first image is now suppressed over here. And this is possible by integrating the information coming from that same region of the sky over a little longer time. So that is called as the integration time. If I still increase the integration time, I can see even much useful information. You can see that there are spiral arms which are discerning out of the central part. Okay, you can see there are number of such spiral arms. Okay, intensity is not, or light is not distributed uniformly throughout this galaxy, but you see there are some well-defined boundaries, or rather what are called as the spiral arms. And if I still further improve the quality, increase the signal to noise ratio, you see that this image is further improved. So this is a typical image which is taken with the help of a 0.5 meter size of a telescope with different integration times like 1 second, 10 second, 100 second, and 1000 second. You can see the effect of the integration time, and that is called as the improving the signal to noise ratio. So we started with that of our science frame, which was a very poor one with not many noise factors involved into it, and finally we have arrived at this clean image. Okay. Now, though we have cleaned it, but is not sufficient, because this information what is available with us is still not directly useful for comparison with that of the information that is shared by other observers. And before that, we have to do again some of the important processes, which is called as a calibration and standardization of the data. And for that purpose, or for deriving even the flux, their luminosity, other useful information like that of the temperature of the objects and so on, we need to do these many standardization. So this process, okay, as far as the stars are concerned, we need to do the photometry of these objects. Excuse me. Okay, I'm sorry. So the science of measuring the flux of the celestial objects is called as the photometry. And to some extent, this photometry is similar to that of your spectroscopy, but it is called as, often it is regarded as the low resolution spectrometry. Okay, so what should we do for the calibration? Here is an illustration. You see the light which is reaching to me. Okay, in addition to that of the background object, once it enters into Earth atmosphere, is affected significantly. Okay, because of the scattering of the photons due to either aerosol or other constituents of the Earth atmosphere, you will find that there are large many number of photons, they are scattered off, they are integrated, means absorbed, and so on. And as a result of which, the light which reaches to us is suffering from these many problems. So before coming to the scientific results, it is required to be calibrated, and that is called as the atmospheric correction, atmospheric extinction correction. Okay, so what we do here, we normally measure the flux of a particular star at different times. This is called as the horizon, okay, and this point is called as the zenith. So over the course of night, you see that the object rises from east and sets towards the west. So what should I do is nothing but I can follow this object regularly after certain intervals of time and take its images. I do the same processing and I compare the magnitudes, I compare the photons that I have collected in the form of electrons generated. Okay, and I after comparing those electrons which are varying as a function of this air mass, because air mass basically is nothing but the equivalent width, or rather what is called as the total net amount of atmospheric loss here over here. If I look at this in this direction, you see that the thickness of this atmospheric layer is very high, and therefore the loss is maximum. And when I look in the zenith position in the exactly overhead manner, I see that the loss is very minimum, and that is the reason why you see the intensity of the same star is going to change as it rises into the sky. Not only that, but you also see that the color of that star is also changing. We do see that the sun at the time of the rise is appearing a very dull reddish kind of ball. Whereas if the same sun comes to the zenith exactly overhead of me, I see that it is very bright and its color is yellowish. So why there is a change in the intensity and why there is a change in the color is because of this atmospheric effect, and we have to take care of it. So how it is done is in the following way. We normally measure its flux. Okay, we also quantify how much is the equivalent thickness of this air column, which is measured in the form of what is known as air mass, and we plot a graph between the two values, and we see this is what I was talking about. The photons, once they enter into the atmosphere, because of the scattering as well as because of the absorption of the photons, it appears to be reddened. Okay, so there is a lot of modification in its emissivity or its emission property. Initially, in the absence of the atmosphere or in the absence of this intervening medium, it was supposed to follow this kind of pattern, but because of the presence of this intervening medium, you see that a large portion of this information is being absorbed out, or rather is removed out. And you see this loss is maximum towards the shorter wavelength side. That means towards the bluer, violet or ultraviolet and so on. And that is the reason why ultraviolet observations need to be performed by putting telescopes orbiting around the Earth, above the Earth atmosphere, about which probably Professor Oza might have discussed with you. Okay, so as far as the calibration is concerned, as I mentioned, I need to follow a star, okay, at different air thicknesses, which is measured as air masses, okay, air mass values, and I can convert that measured value into a magnitude scale, which is nothing but minus 2.5 times log of the flux that I measure, the number of free electrons which are generated over here. So you can see this, and I can measure the intercept of it, I can measure the slope of it. So this slope of this curve, plot between the air mass versus observed magnitude is illustrated by means of this equation. M naught is equal to m minus kx, where k is the slope and intercept is taken as m naught. So I can find out m naught as well as what is called as the slope of this curve. So this slope of this plot, and this slope is nothing but the extinction value. Okay, so you see that the extinction which is measured for this V band for this particular observation is of 0.149 value, whereas for the B band it is about 0.237. So can you see these figures over here? Hello.
Yes, sir. Yes, yes.
So you see that this value is 0.237, whereas here it is 0.149. It is lower for the V band, and here it is slightly higher. So as I mentioned, it is a highly wavelength dependent factor. Okay, shorter the wavelength, more is the loss, and vice versa. Okay, so by doing this kind of analogy, we can apply this correction due to the loss of the photons in the Earth atmosphere, and the effect of Earth atmosphere can be seen even in the scientific manner called as the seeing condition. So seeing basically is nothing but indicating the atmospheric condition at the time of the observation. You see, this is a photograph taken with that of the telescope and CCD camera, and you can see some isolated stars into it. Okay. If the seeing is very good, you see that the extent over which this image is spread is very, very, very small. Okay, here is seeing equal to 0.8 arc second, whereas here you see the seeing is 1.5 arc second. So under the conditions of 1.5 arc second seeing, you see the image.
Hello.
Observing conditions or other sites and do imaging with that of the better conditions. Now, as far as the photometry of the stars in this frame is concerned, we can consider a star at a time and collect the photons which are falling within this particular portion by selecting some aperture, and we can do the photometry. So if I plot its intensity variation in the two-dimensional form, okay, this is x direction, and let us say this is y axis, and here you can see these pillar-like structures which are nothing but the intensity of that particular star. Okay, and this is the background. You see, still there is a background, and this is what is the noise. We have to remove this background. I will show some beautiful images which are corrected for the background. In this image, you see there is a light streak like this, and if I take surface plot of this object, you will find that it is appearing something like this. Okay, there is a tall building like this, and then it is almost a flat. And remember, or believe me, it is a faulty image, or the object has a very high intensity, and therefore the capacity of that pixel under on which these photons were incident is exceeded, and that is the reason why it is spilling over the neighboring pixel, and that is what is the saturation of the CC. Okay, so such saturated images are of no use for us because they cannot produce or rather enable us to derive a fruitful information of topic. So as far as the photometry was concerned, you see that the individual star we can consider here for doing photometry. Here is the star, and here is the aperture that I have set for extracting its counts. So this is the plot which shows how this intensity is varying in this region. But remember here, though I am considering a very, very small portion, okay, you see it contains the counts coming from that of the star, as well as there are some background counts. And we need to remove these background counts because they are of no use for us, rather they are worsening our result. And in order to improve it, we have to subtract it. So how should I do, or what should I do? So for that purpose, what I will do, I will take the same aperture to some other portion of the CCD image where there were no stars. For example, if I select a portion somewhere here, okay, so they are assuming that there are no stars, I can take the count level there. Okay, so this is a purely background, you see here. So this is the B portion over here, and it is a perfectly background. I can subtract this background value from that of the sky plus star counts, and then I get purely the photons which are coming from that of this particular star only. And then this is a very clean image wherein you can see that the background is almost constant, which is having a very, very, very low value. And this is the brightness distribution, the surface plot of this star. And you can see that it is a coming up like that of a Gaussian pillar over there. Okay. So if I plot its intensity variation as a function of a radius, that is called as a radial plot, you see at the center it is a maximum, and as I go to the outer side, for example, if I come over here, you see it is reaching to this level, and beyond which it is almost remaining constant. So this constant value is called as the background, which I can either calculate manually or by doing some sort of computer programming, and you see that this constant value can be subtracted very easily as a background. Okay, but how big should I select the aperture? That is very important, because if this is the size of my object, and if I am taking a aperture of very big size, that is of no use. Rather, it will be again worsening our results, and therefore it is again means a very careful analogy that we have to select the aperture size as appropriate to our observations. So once we take the clear counts or the cleaned counts, then we can convert it into some magnitude scale. Okay, and as if you look at this equation, you will see that the magnitude is defined as minus 2.5 times log of the counts over there, and because of this negative sign, you see that the smaller the number, brighter will be the object, and vice versa. Okay, so I will skip some of the slides over here because I'm running short of time now. So how to standardize the data then? Okay, because the telescope which I have used, the detector which I have used, and the filter setup which I have used is giving rise to some component which is giving rise to some magnitude, and that magnitude is called as the instrumental magnitude. And I need to standardize it because before comparing it with that of the results provided by that of the others. So how to do it? And for that purpose, we have to observe some sort of what are called as the standard fields, which are called as the standard stars. This is a typical field of SA98, which is called as a Landau field. And you see that these green circles are covering some stars which are well studied. So I can observe the same stars. I can derive the instrumental magnitude for individual stars from this field, and then I compare it with those which are published, which are available in the literature, or which are called as the standard values, and then from which I can plot such type of graphs between the these big values, means capital values. B minus V are nothing but the standard values which are reported, which are available in the literature, and these small values are nothing but my cleaned or calibrated values after doing all sort of pre-processing over there. And then by deriving the slope of these curves and using such type of transformation equations, I can now obtain these slope values as well as the intercepts, and these are nothing but the transformation coefficients for my instrumental magnitudes. Just like that, we cannot use any stick for the measurement of length of an object. Rather, it is to be calibrated properly in the form of the marks onto it. In the same way, our raw data, now we have to standardize by making use of these equations, and these equations stands as the calibration or the transformation coefficients. So this is all for the true for the individual objects, isolated objects, which are called as the stars like objects. But what about the extended object? For example, if I go to the object like this is called as a globular cluster, where you see that there are millions of stars within this field, and I cannot do the photometry like that, what I did earlier for individual star. So here my approach should be something different, and what is that approach? I wanted to talk with you. So there could be some objects, something like this also. These are the galaxies, which are themselves, they are comprised of billions of stars. Okay, again, there could be galaxies, something looking like this. So this galaxy and this galaxy, they are very significantly different. So how to perform their study? Okay, and for that purpose, what we do basically is nothing but, instead of the aperture photometry, what I talked earlier for individual star, here we do the surface photometry. So in this surface photometry, you see that the flux that I am measuring and the solid angle that is subtended by my detector, as both they are going as 1 upon r square. Therefore, when I take the ratio, so the distance dependent factor is taken care, and therefore whatever magnitude I get is again useful for doing the similar study, but for the extended object, and that is called as the integrated magnitude. Okay. So the colorful images, what we see normally in literature, they can also provide information to us, but this information is by assigning some pseudo colors to them, or by taking the 3 different images in 3 different filters. by taking images in red band, green band, blue band, then we can add them together and we can obtain a very beautiful image like this one. So this is something, a region which is called as a star forming region in the sky, and it is basically the combination of these three images. So there you can see plenty of such images which are available in the literature, in the handouts, in the websites, and so on. So all these images, they are the tricolor images acquired using three different filters, and then they are accordingly added together, co-added together rather, and they finally produce a set of beautiful pictures, which of course gives you information regarding the colors also. So this bluish color means it must be a hotter region, the reddish must be a cooler region. So this kind of information is one can extract with the help of this one. Similarly, we can do a similar process for even the galaxies also, and we can derive such type of beautiful images out of it, which eventually give you information regarding that of the dust patches, dust features which are embedded within it. You can see the stellar distribution, the young population, older population at the center, and whatnot. So all this information we can obtain with the help of the images, not only in optical passbands, but even in infrared as well as the ultraviolet band, which probably Professor Oja might have discussed with you. So we can also use a lot of processing techniques like that of the wavelet transformation. We can detect the images, we can detect illusion objects within it, and so on. Okay, but I want to go a step ahead, and I want to tell something else to you regarding this extended object. So as far as the extended objects are concerned, this is a galaxy which is called as elliptical galaxy. This is also a galaxy, but it is called as a spiral galaxy. If you look at these two galaxies carefully, you see that this galaxy is very interesting. Okay, you can find a very bright nucleus at the center. There is some somewhat fainter region over here. Then there is again a brighter region surrounding to it. And interestingly, if I can look at these features, they are not uniformly distributed. Rather, they are forming the spiral arm-like patterns around the central part. So you see that this portion basically is nothing but the spiral arms, and it is a very rich in interstellar medium, dust, and other things. Believe me, this dust, though it is a very small fraction of the interstellar medium, is a very important ingredient for the star formation. So wherever we find such dust features, we can guess that there must be some sort of star formation activity might be going on. No doubt, it may be varying in the scale of the star formation, but still there is a hope to say that the star formation might be taking place at such type of places. So if I look at this galaxy and compare it with that of this galaxy on the right side, you see that this is a very uninteresting kind of object. It is simply a collection of light. There is no any hidden features into it. There is no any star region, nothing. Okay, and that is the reason why these galaxies, they were regarded as that of the red and dead kind of systems. They are still now they are referred to as the early type galaxies, and they are very simple structures of the cosmos. Okay, so they are very different. They are different not only in the morphological form, but they are also different because of their formation scenario. Okay, so if we study these galaxies systematically and we do the photometric studies, or we do some sort of other image processing onto it, we can not only study the features of the different parts of it, but we can also tag the information regarding their formation as well as evolution. So how it is possible to get the information regarding the evolution or formation of this galaxy, which has formed billions of years ago? That is a very interesting thing, and we can do it with the help of the image processing. So this is the same image. What we can do, we can fit the isoforce. Isoforce means iso intensity. The same intensity contours, we can join the points of the same intensity in this image with the help of the IRAF, and we can fit the ellipses to it, assuming this what is called as the Fourier analogy, that the intensity at any point is the sum of these many components. And by doing this image processing, by fitting ellipses to the iso intensity points, we will see such type of ellipses over here. And these ellipses, this process is called the ellipse fitting. And for the details, you can either look at this reference, or there are quite a few references which are available in it. Okay, so if I do the ellipse fitting, I will get some such type of plots, out of which these 2-3 plots are very important for me. So what is this plot? Is nothing but the plot which shows how the intensity is varying as I go from the center to the outward. For example, this is the center of the galaxy, and as I go along this semi-major axis, this is called as the semi-major axis, and this is called as the semi-minor axis. So when I go from the center outward along the semi-major axis, how does this intensity fall? That is depicted by means of this plot, and it's called as the surface plot, surface intensity plot, or it is called as a surface brightness plot. Okay. And this is very interesting plot, which you see that the ellipticity is basically nothing but the ratio. It is based upon the ratio of this major axis and minor axis. And you see it is not constant, rather it is increasing up to this point and then is changing. Moreover, there is another very important plot which is called as the position angle. So how are these ellipses oriented within the image itself? That can also be studied with it. And believe me, if I do a systematic study of these isophores, I will find that in some galaxies, those isophores may appear like this or may appear like this. So these galaxies which exhibit the isophores of this kind, the ellipses of this nature, they are called as the boxy galaxies, and these are called as the disky galaxies. Believe me, again, this origin of these boxy isophores or boxy elliptical galaxies and disky elliptical galaxies, they are altogether different and are again very interesting things. One more important analogy which one can do with this ellipse fitting process is the following. For example, if you look at this satellite galaxy of our Andromeda, the neighboring galaxy, you see that this is a shallower image which is taken with that of with small integration time. Only the central part of that galaxy is visible, and you see that it is a very beautiful elliptical galaxy. So if I fit ellipses to it, okay, from center to the outward, so you see they are the concentric ellipses systematically arranged on the basis of their decreasing intensity level. But if I look at the same galaxy, okay, if I take a deeper exposure of it and look at this same galaxy and perform the same analysis, I see that the ellipses which I am fitting to it, they are not aligned in the same way. Moreover, their ellipticities are not same. Their orientations are different. And such type of galaxies, they are called as the traxal galaxies. And you see in the inner portion, the orientation of the ellipse was something like this. Here it is like this. Here it is like this. Or in other words, it is showing a pattern, something like this. So if I go into the detailed study of it, you see that this is exhibiting some traxal nature. And not only that, there are some spiral elliptical galaxies, of course. If I take the deep images of them, if I integrate the information coming from these galaxies for a very long time, you see that these are not only showing this brighter central part, but there you can see such type of ripples. And these ripples are the signatures of their formation through the merger of several spiral galaxies. This is again another you see mosaic of a number of images of the galaxies, which are of course the elliptical galaxies with not many features into it, and these features are the dust features. Will you remember in earlier discussion I stated that the elliptical galaxies are the simple galaxies which do not host any dust planes or any other features, but you see that these galaxies, they do host the dust planes also, and hence we can study their properties by deriving their model. By fitting ellipses, we can derive a very smooth model of it, and if I divide them or if I subtract from one another, I can arrive at such type of results, and these results are called as extinction maps. Okay, so the brighter patches, brighter shades here, they indicate the presence of the dust lanes, and by measuring what is the magnitude at these locations using this particular equation, I can quantify how much is the loss of light that is taking place in it because of the presence of dust, or in other words, I can quantify the level of the dust present over there, the quantity of the dust present over here, and I can also compare it with that of the other images, and I can see the effect as a function of the element. So this is a B band image, V band image, R band image, and I band image, and you see that the effect is maximally seen in this case compared to that of the other one. So by studying such features and by plotting the curve with that of the Milky Way, we can see that this is a beautiful graph which we can plot, and is called as the extinction curve. And this extinction curve tells you the properties of the dust particles which are present in other galaxies. Remember, these galaxies are far away from us, millions of parsec away from us, but still by making use of bigger size telescopes and studying them systematically, we can not only study their presence, but we can go a step ahead and we can calculate what are the grain sizes they are responsible for this loss. Okay, so this is a very interesting science what one can derive out of it. So this is again one beautiful example of NGC 1482, where you can see the dust features, we can study it, we can calculate the mass of dust present into it. And if I know what is the dust content of it, I can calculate even the star formation rate. So which means that the elliptical galaxies, early type galaxies, which otherwise were believed to be the very simple galaxies, without any dust, without any other features, now they appear to be very interesting. They are still forming stars, they are still hosting dust particles and so on. If I compare their properties with that of other emission wavelengths, for example, this is the H alpha, green is the H alpha and blue is the X-ray. So X-ray part is found to be extended and is orthogonal to that of the optical part. That means they might be having different origins. So there are several such interesting results that are available in the literature, and we have studied a couple of several such galaxies as a part of our study. And this is again one very beautiful example, very interesting example here. So there are many such results which I can skip because I'm already crossing my time limit. This is a again a mosaic of the galaxy NGC 5128 Centaurus galaxy, taken in different bands, and you see that it provides a lot of different kind of information through it. Okay, therefore, in order to arrive at a science, we need to perform observations not only at a single wavelength, but we have to observe the objects at multiple wavelengths and then correlate them compare their properties and arrive at what is called as the important science. So what is the takeaway from this presentation is nothing but the image processing is an art of deriving science from the raw astronomical images. So it is one of the very effective tools of the modern astronomy. Data, which I have already mentioned, is very noisy. It need to be cleaned, it need to be calibrated, it need to be reduced using some packages like that of the IRAF. Then we have to calibrate and standardize it, and then identify the features by making use of a lot many image processing techniques like that of visual inspection, color index maps, quotient images, unsharp masking, extinction maps, and so on. I'm very sorry because of lack of time, I could not focus on some of the important aspects which I was supposed to do. Okay, so these are a couple of resources which are available. You can go through them and you can have a fun with them. Thank you very much.
Thank you very much, Patel sir. Some questions from students. We have one question in chat box.
Yeah. If there are questions, I will be very happy to at least give my view out. Yeah.
From Adil Singh, what is the special resolution of modern infrared telescope?
Hello.
So there is one question in chat box.
Yeah. Yes.
What is the special resolution of modern infrared telescope?
Special
resolution of modern infrared telescope.
Special resolution. Okay. See, the special resolution of the infrared telescopes is relatively poor compared to that of the optical, means the visual. Okay, and it is because of the scattering of the photons into the atmosphere, as I have already mentioned. It is called as a seeing effect. So as the aerosols and other heavier particles, they have the wavelengths, means their sizes comparable with that of the wavelength of the infrared photons, and that is the reason why scattering effect is more there, and that is the reason why the resolution of the infrared images or telescopes are relatively poor. Of course, they would be of the order of a few arc seconds. Yes.
Right. And another question is, what is the possible origin of cosmic neutrinos?
Cosmic rays.
Cosmic neutrinos.
Cosmic neutrino. Okay. Neutrinos, see, they are the product of some other processes. For example, you know, at the core of the sun and sun-like stars, many processes are taken, particularly the energy generation is taking place through a thermonuclear fusion process, wherein protons are fusing. Okay, and during this process of fusion of protons and converting it into the alpha particles or helium nuclei, there are some byproducts which are very energetic and less massive. These are called as the neutrinos, which will be escaping out of the sun because they are least interacting, as I have mentioned, and therefore they will be arriving often to even Earth also. Yeah.
Right. So, okay, sir. Thank you very much for a wonderful talk. And you have covered
Thank you very much.
the telescope, and you have also covered the regarding instruments like CCD, photometry, and spectroscopy, and you have also covered all the protocol of the data analysis.
Oh,
Very
actually,
wonderful.
that was my focus. I wanted to start with that
Elaborating
observational
talk. So,
Yeah.
so thank you very much, sir. Participant,
Thank
very
you. And indeed, it has been my great pleasure to interact with you all, though it is a virtual platform. And thank you very much once again for giving me this wonderful opportunity to share some of the information regarding this image processing. Thank you. Thank you very much.
Now we close the today's last session. Okay, thank you very much to all participants. You also. Okay, thanks a lot.